Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. In the silent depths of space, there are wanderers. From the faintest dawn of history, human eyes gazed upward at bright points of light that moved against the fixed stars. The ancients called them planets, meaning wanderers, imagining gods and myths trailing across the night sky. But beyond the poetry of ancient minds, what truly is a planet? It is more than a mere light in the sky. It is a world unto itself. Planets are the great wanderers of the cosmos, worlds shaped by fire, gravity, and ice, each with its own story, written in molten rock and swirling cloud, in howling wind and drifting snow. They are the children of stars, born from cosmic dust and pulled into spheres by the inexorable embrace of gravity. They orbit in darkness, illuminated only by the suns they circle, and yet each holds its own internal light. The warmth of formation or radioactive decay, the glow of volcanoes, the electric crackle of storms. They range from scorching spheres of rock to bloated giants of gas, from oceanic blue orbs to frozen balls of ice and stone. Some are ensconced in thick blankets of cloud, others naked under the cosmic night. Some, incredibly, are lonely nomads, drifting between stars with no sun to call home, true wanderers in eternal night. To be a planet is to dance in a delicate balance. It means to circle a star in a cosmic rhythm, held by gravity's tether yet ever, falling around the light. It means to be round, sculpted into a globe by one's own gravity, mostly smooth, yet often scarred by the battering of eons. It means to dominate a little corner of space, clearing a path through smaller debris. Planets come in families, solar systems, where each member plays its part in the celestial choreography. Our own family is the solar system, with the sun as the patriarch and planets as its heirs, moving in regal procession. Imagine drifting high above the plane of our solar system. Below, the sun burns as a golden beacon, and around it, like marbles on invisible tracks, the planets sweep through space. Mercury, closest to the sun, is a little burnt cinder racing along its tight orbit. Venus follows, wreathed in thick, toxic clouds reflecting sunlight like a jewel, hiding hellish heat beneath. Earth, our home, blue with oceans and white with clouds, teems with life, our oasis in the dark. Mars comes next, a ruddy desert with ghostly dust storms and polar caps of frost, whispering of a wetter past. Far beyond, a belt of asteroids forms a rough boundary, and then the giants take the stage. Jupiter, king of planets, streaked in bands of stormy color, guards a menagerie of moons. Saturn, with its shimmering rings of ice, elegant and enigmatic. Uranus, tipped on its side, rolling around the sun with a pale cyan hue. Neptune, deep blue and distant, where supersonic winds drive dark storms. And at the edge, small icy worlds like Pluto circle in shadow, blurring the line between planet and comet in the distant Kuiper belt. These are the known members of our Sun's family, 8 major planets by the modern definition, and a host of dwarf planets and countless smaller bodies. Yet planets are not unique to our Sun. As our knowledge grew, we discovered planets orbiting other stars by the thousands. We realized our night sky is filled with other suns, each with their own retinue of worlds. Planets, it turns out, are abundant in the galaxy. Perhaps every star has at least one, and in total, they likely number in the trillions. Some of these exoplanets are familiar in outline, rocky Earth-like bodies or gas giants like Jupiter, but others are stranger than we ever imagined. Giants so close to their stars that their skies rain molten iron, or worlds locked in eternal ice, far from any warmth. There are even worlds that wander alone, rogue planets drifting in perpetual darkness, having been thrown free from their stellar birthplace. The cosmos is literally overflowing with planets of every kind, each a chapter of the grand story of creation. This journey will explore what it means to be a planet from multiple angles. We will trace the historical path, from ancient stargazers to the scientific revolution that revealed Earth as a planet, and the later discoveries of Uranus, Neptune, and Pluto's reclassification, a saga that redefined our cosmic perspective. We will visit the inner solar system, the terrestrial planets, small spheres of rock scorched or nurtured by the sun, each with a unique personality. Mercury's extreme heat and cold, Venus's runaway greenhouse inferno, Earth's living biosphere, and Mars's lost rivers and thin air. Then we venture to the outer solar system, colossal gas and ice giants with raging storms and delicate rings, and moons that might hide life beneath their icy crusts. We will meet the dwarf. Planets like Pluto, Eris, and Ceres, diminutive worlds that challenge our definitions and remind us how diverse planets can be. Beyond visiting each member of our solar family, we will delve into the processes that shape all planets. We'll witness towering volcanoes that spew fire and shifting tectonic plates that mold the lands. We'll examine impact craters, the scars of cosmic bombardment, and winds and water that erode and change landscapes over eons. We'll peer into atmospheres thick and thin, the crushing yellow haze of Venus, the thin, cold sky of Mars, Jupiter's banded clouds, and Titan's orange smog. We'll experience weather and climate extremes beyond any earthly storm, from Jupiter's great red spot that has raged for centuries to the 1,200 mile-per-hour winds of Neptune that whip methane clouds into streaks. We will also uncover the hidden magnetic fields and internal structures that many planets possess. Those invisible shields born from molten cores or metallic hydrogen that can deflect deadly solar winds, and the strange interiors where pressures soar and matter behaves in exotic ways. And as our voyage extends outward, we will leave the comfort of our solar system entirely to discover exoplanets in their astonishing variety. We'll classify these alien worlds, super-Earths, hot Jupiters, mini Neptunes, rogue planets, and more, and see how they broaden our understanding of what a planet can be. We'll ponder the conditions that might make a planet habitable, able to support life, and how scientists seek the faint fingerprints of biology on worlds light years away. Finally, we'll look ahead to future exploration, the upcoming missions and bold ideas to visit new worlds, to send robot emissaries or even humans to planets and moons, and to build telescopes capable of reading the atmospheres of Earth like planets around distant suns. And throughout this odyssey, we will reflect on philosophical questions. What do these diverse worlds teach us about our own existence? How has the study of planets changed the way we see ourselves and our place in the universe? In exploring alien worlds, we inevitably hold up a mirror to Earth and to humanity. So, let us begin where our ancestors once did, by seeking to understand the wandering lights in the sky, and in doing so, embark on a journey across the solar system and beyond. Our first stop is the story of how we came to know these planets at all, a tale of curiosity, observation, and the courage to question our place among the stars. From myth to discovery, a history of our understanding. For most of human history, planets were points of light, their true nature unknown. In antiquity, 5 wanderers were known: Mercury, Venus, Mars, Jupiter, and Saturn. These wandering stars were held as gods. Mercury was the quick-footed messenger, Venus the goddess of love, shining as morning and evening star, Mars the blood, red warrior, Jupiter the king of heaven, and Saturn the god of time. The sun and moon were counted among the planets in the old world view, and Earth was not a planet at all, but the fixed center of creation. In ancient Greece and Rome, and in civilizations as far-flung as Babylon, India, and China, Elaborate cosmologies placed these 7 wanderers on crystal spheres or chariots circling the Earth. Their motions were mysterious but meticulously observed. Occasionally, Mars would retrograde, moving backward against the stars, confounding expectations. To ancient astronomers, the planets were divine oracles whose motions foretold omens and seasons, yet their physical nature remained a subject of philosophical speculation. Aristotle and Ptolemy believed in a geocentric cosmos, the planets, sun and moon revolving in perfect circles around an unmoving Earth. It took bold imagination and careful observation to break this geocentric spell. In the 16th century, Nicholas Copernicus proposed a revolutionary idea. The sun, not Earth, was the center, and Earth itself was just another planet circling the sun. This heliocentric model demoted Earth from its special pedestal and made it one of the wanderers. It was a radical, even heretical thought at the time, challenging both scientific and religious dogma. But evidence soon began to accumulate. In 1609, Galileo Galilei turned the newly invented telescope to the heavens and witnessed wonders that forever changed our understanding of planets. He saw that Venus goes through phases like the moon, waxing and waning in shape, which only made sense if Venus orbits the sun, not Earth. He discovered 4 moons circling Jupiter like a miniature planetary system, a clear sign that not everything revolved around Earth. And he observed the rugged mountains and craters on our moon, showing celestial bodies were not perfect ethereal orbs, but had landscapes and geology. Galileo's telescopic revelations gave tangible reality to planets as worlds, places that could be seen and studied, not just lights. With the Copernican paradigm taking hold, astronomers realized that Earth was a planet too, moving through space with the rest. This was a profound philosophical shift. Humanity had to accept that our world was one among many. Over the next centuries, the solar system's known architecture expanded. In 1781, William Herschel, scanning the sky with a powerful telescope, noticed a tiny disk rather than a point. He had accidentally discovered Uranus, the first new planet found in recorded history. At first, Herschel thought it might be a comet, but its slow, steady orbit revealed it as a planet beyond Saturn. The solar system now had 7 planets. The discovery of Uranus doubled the size of the known solar system and suggested there could be more unseen worlds farther out. Uranus's orbit itself held clues of something more. By the early 19th century, astronomers noticed Uranus did not move exactly as predicted. It was being subtly tugged by an unknown force. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that an 8th planet must be lurking farther out, its gravity perturbing Uranus's path. In a triumph of physics and astronomy, Neptune was discovered in 1846, almost exactly where the calculations predicted, by Johann Galle and Heinrich Darest at the Berlin Observatory. Neptune was dim and distant, invisible to the naked eye, yet the power of human reasoning had brought it to light. Now the known planetary count was 8. Around the same period, another kind of planet was found in the gap between Mars and Jupiter. In 1801, Giuseppe Piazzi discovered Ceres, a small world orbiting where a much larger planet might have been expected. Soon, Pallas, Juno, and Vesta were found, more small bodies in that zone. At first, Ceres was called a planet, but as dozens more of these objects were detected, it became clear that Ceres was the largest of a whole belt of minor planets, not a lone new world on par with the others. By the mid-19th century, school textbooks briefly swelled the planet count to as high as 11, only to drop back down as Ceres and its kin were reclassified as a separate category. The word planet came to be reserved for the major bodies that dominated their orbits. By the turn of the 20th century, the solar system's 8 primary planets were well known, but some astronomers suspected there might be yet another planet lurking beyond Neptune, Planet X, as it was dubbed. Percival Lowell, an American astronomer, hunted for this theoretical planet in the early 1900s. driven by hints of irregularities in Neptune's motion. Lowell did not find it, but after his death, the search continued at Lowell Observatory in Arizona. In 1930, a young astronomer named Clyde Tombaugh systematically photographed the star fields of the ecliptic and painstakingly looked for anything that moved. On a cold February day, Tombaugh found a dim speck that shifted position against the stars. It was the long-sought planet X, soon named Pluto, after the Roman god of the underworld. The public was enthralled. Pluto was hailed as the 9th planet, a tiny, distant oddball in the solar system's outer reaches. For much of the 20th century, the solar system was taught as 9 planets, Mercury through Pluto. But as telescopes improved, especially towards century's end, we began to find more objects orbiting out near Pluto. In 1992, the first of many Kuiper Belt objects was discovered not far from Pluto's orbit, implying Pluto was not a lone maverick, but part of a larger population of small, icy worlds. The trickle of discoveries became a deluge in the 2000s. Then, in 2005, astronomers announced Eris, an object about as large as Pluto, far beyond Pluto's orbit. Suddenly, our neat conception of the solar system was challenged. If Pluto was a planet, why not Eris? And what about the other large Kuiper Belt objects like Makemake and Haumea being found? The field reached a crossroads. In 2006, the International Astronomical Union took a vote in a meeting that echoed around the world. They formally defined the term planet for the first time. According to the IAU, a planet must orbit the Sun, be massive enough for its gravity to pull it into a nearly round shape, and have cleared the neighborhood around its orbit. By that definition, Pluto failed the third criterion, since it shares the outer solar system with many similar icy objects. Pluto was reclassified as a dwarf planet along with Eris and Ceres. Overnight, the solar system went from 9 planets to 8. The decision was contentious. Many in the public lamented the demotion of Pluto, and even some astronomers disagreed, pointing out that Earth, Jupiter, and others still have small neighbors in their orbits. The debate over what constitutes a planet continues philosophically, but in practice, the new terminology stuck. We now speak of the 8 classical planets and a growing menagerie of dwarf planets. This historical journey, from the earliest recognition of wandering stars, to the Copernican revolution that made Earth a planet, to the telescopic discoveries of new planets, and finally to the reclassification of Pluto, shows how our understanding of planets has evolved with our knowledge. We moved from an Earth-centered universe to a Sun-centered solar system, and then to a vision of countless solar systems in our galaxy. Each step required us to redefine our place in the cosmos, and even as we debated definitions, we learned that nature resists rigid categories. Planets come in a continuum of sizes and orbits. The line between planet and not planet can be blurry at the edges. The story of how we came to know the planets is a story of curiosity, persistence, and a willingness to change our perspective when confronted with new evidence. Having placed ourselves among the planets and traced their discovery, we now turn to explore the planets themselves as worlds. We begin with the inner solar system, those rocky neighbors of Earth that bask closest to the Sun's fire. The inner worlds: Mercury, Venus, Earth, and Mars. We begin our planetary journey with the inner solar system, a realm of sun, baked rocks, and metal. These are the terrestrial planets, small, dense, and composed mostly of silicate rock and iron. Born of similar materials and initially not so different, they have since diverged into 4 dramatically distinct worlds. From airless craters to runaway hothouses to a living blue oasis and a frozen desert, the inner planets show how varied outcomes can be even among sister worlds. Mercury, the closest planet to the Sun, is a little grey furnace of extremes. It is the smallest of the 4 inner planets, only slightly larger than our Moon. Like the Moon, Mercury's surface is heavily cratered and ancient, recording a violent history of impacts. There are brilliant ray crater patterns splashed across its dark grey terrain, and enormous basins from asteroid collisions long ago. Mercury has almost no atmosphere, just a whisper of atoms blasted off its surface by the sun's radiation, so nothing shields it from meteoroids or evens out its temperature. Daytime on Mercury is blistering, hot enough to melt lead, but the night plunges into frigid darkness since there is no substantial air to trap the heat. A Mercurian day lasts 2 Mercury years long, because Mercury rotates slowly and orbits fast. This results in oddities. If you could stand on Mercury's surface, you would see the sun blazing huge in the sky, rising and setting in a slow, drawn-out dance, even briefly reversing course around sunrise due to Mercury's orbital resonance. Inside, Mercury is a world that punches above its weight. Despite being so small, it is incredibly dense, almost as dense as Earth, because it contains a gigantic iron core occupying most of its interior. This core, spanning about 3/4 of the planet's diameter, generates a magnetic field around Mercury, albeit a feeble one only about 1% as strong as Earth's. Still, it's remarkable that this tiny, slowly rotating planet maintains any magnetic field at all. Mercury's iron heart also hints at a dramatic birth. Perhaps it formed from normal proportions of rock and metal. But a titanic impact early on stripped much of its rocky mantle away, leaving a metal, rich remnant. On Mercury's surface, the evidence of an active past includes long scarps and cliffs, some hundreds of kilometers long and soaring up to a mile high, that crisscross the terrain. These formed as Mercury's core and mantle cooled and contracted, wrinkling the crust above. Volcanic plains, now solidified, also exist, indicating that billions of years ago, lava once flowed across Mercury's surface. But for at least the last few billion years, Mercury has been geologically quiet, a bare, inert world of extremes. It is a planet essentially without air or water, where the landscape is carved only by impact and the slow thermal cracking of sun-baked rocks. In the brilliant morning sun, the ground would be blinding and dead silent, and at night, the stars would burn cold in a black sky over a landscape as still as a tomb. Leaving little Mercury and moving outward, we encounter Venus, often called Earth's twin in size and composition, but in reality, a twisted mirror image of Earth, similar in bulk, yet utterly hellish in condition. Venus is almost exactly the same size as Earth and formed in the same neighborhood of the Sun, presumably with similar ingredients. It likely started out much like Earth, with volcanoes, a thick atmosphere, and possibly even oceans. But at some point, Venus took a divergent path and fell victim to a runaway greenhouse effect. Today, Venus is a world enshrouded in dense, yellowish cloud, its surface hidden from view in visible light. That thick atmosphere is composed overwhelmingly of carbon dioxide, with clouds of corrosive sulfuric acid droplets whipping around the planet. The weight of Venus's atmosphere is enormous. At the surface, the pressure is about 92 times that of Earth's sea level. This heavy blanket has trapped so much heat that Venus's surface is the hottest in the solar system, around 464 degrees C everywhere, day or night, pole or equator. It is hotter even than Mercury, despite being nearly twice as far from the Sun, solely because of the greenhouse gases that lock in the Sun's heat. In essence, Venus shows what happens when a planet's heat balance goes awry. Sunlight passes through the clouds, heats the surface, and the infrared heat cannot escape efficiently due to the CO2, causing a feedback loop of warming. Long ago, Venus might have had temperate conditions, but as the Sun grew brighter over eons, Venus's oceans likely evaporated, and water vapor helped drive temperatures up until the ground itself baked out carbon dioxide from rocks, filling the air with CO2 and turning the planet into a pressure cooker. If you could descend through Venus's clouds, you would find the light growing dim and orange, tinted by the sulfuric haze. By the time you reached the ground, it would be twilight at midday, and the air would be a toxic yellowish fog, so thick it feels almost like a fluid. The heat would be instantly overwhelming, high enough to melt lead, and certainly high enough to melt any lander electronics within an hour or two. The landscape, as revealed by Soviet Venera landers and radar mapping from orbit, is a rolling desert of orange, red rocks, and vast volcanic plains. Venus's surface has mountains higher than Everest and great plateaus, as well as thousands of volcanoes, from huge shield volcanoes to innumerable small cones. The terrain has strange features called coronae, circular patterns hundreds of kilometers wide, believed to be caused by upwellings of magma pushing on the crust. Yet surprisingly, there are few impact craters. The relative lack of craters tells us Venus's surface is geologically young, maybe only 500 million years old. Planetary scientists suspect that Venus underwent a global resurfacing event, perhaps massive volcanism that paved over older terrain, and it may still be volcanically active today. In fact, recent studies of old radar images have shown hints of change in some calderas, suggesting an ongoing eruption, and the Venusian atmosphere contains mysterious chemistry hinting at active volcanoes. However, Venus has no plate tectonics like Earth. Its crust appears to be one giant stagnant lid, which might periodically break down in outbursts of planet-wide volcanism, essentially repaving the planet in floods of lava. Beneath the surface, Venus likely has a metallic core and a mantle similar to Earth's, but unlike Earth, it spins extremely slowly. A Venusian day is 243 Earth days, and curiously, it spins backwards. This sluggish rotation is likely one reason Venus has almost no magnetic field. Without a protective magnetosphere, the upper atmosphere of Venus is constantly bombarded by the solar wind, which slowly strips away lighter molecules. Yet the atmosphere is so thick and heavy that losing some particles to space hardly dents it. Standing on Venus, you would experience a bizarre scene, a dim orange glow in all directions through the haze, the air utterly still near the ground, and a forbidding, silent landscape of rocks and gently sloping volcanic plains. It is an infernal environment, the closest thing to a vision of hell on any planet, and a stark warning of the power of atmospheric chemistry gone wrong. Traveling onward, we arrive at our own planet, Earth. It might seem unnecessary to describe Earth among its neighbors, but viewing Earth as a planet, one of many, is key to understanding what makes it special. Earth is the only planet we know of that hosts life, and not just a few microbes, but a rich biosphere of complexity and diversity, including us, who can marvel at that fact. Several factors conspire to make Earth a haven amid the void. It orbits in the habitable zone of the Sun, where temperatures allow liquid water to persist on the surface. Our planet is just large enough to hold onto a substantial atmosphere, but not so large as to become a gaseous giant. Earth's surface is a mosaic of blue oceans, green and brown continents, and white clouds, a dynamic, ever-changing patchwork, sculpted by both geological forces and living organisms. Unlike the rest of the inner planets, Earth's crust is divided into moving plates, an evolving jigsaw puzzle riding atop the slow churning of the mantle. This plate tectonics is a geological wonder. Continents drift, collide, and separate. Earthquakes rumble along faults. Volcanoes emerge where plates diverge or converge. Over millions of years, this process rejuvenates the surface, builds mountains, and recycles carbon, and may be crucial in regulating Earth's climate over geologic time. Indeed, plate tectonics, with its ability to bury carbon, rich sediments, and then release CO2 via volcanoes, acts as Earth's thermostat, keeping temperatures within a range that allowed oceans to remain liquid for billions of years. Earth's atmosphere is a unique mix: 78% nitrogen, 21% oxygen, plus traces of other gases like argon, carbon dioxide, and water vapor. That oxygen is a direct product of life. Photosynthetic organisms have been exhaling it for eons. The atmosphere is dense enough to buffer the surface from small meteoroids and to distribute heat around the globe. but thin enough that our planet isn't smothered in crushing pressure. It gives us a mild greenhouse effect, enough to keep the oceans from freezing solid, but not a runaway like Venus. And it shields us from deadly solar and cosmic radiation, especially thanks to Earth's magnetic field. Generated by a rotating, convecting liquid iron core, our magnetic field forms a protective bubble that deflects charged particles from the Sun. Where some of those particles do leak through near the poles, Earth offers a dazzling light show, the auroras shimmering green and red in polar skies. Earth's magnetic field, plate tectonics, and moderate atmosphere all work in concert with the Sun's favorable distance to create a stable, life-friendly environment. In that stable environment, water could remain liquid and life could take hold. Life, in turn, transformed the surface and air, covering once barren rock with soil and foliage, and pumping out oxygen to create an ozone layer protecting the surface from ultraviolet rays. From space, Earth is a shimmering blue marble with swirling white weather systems, a striking contrast to the monotonous clouds of Venus or the rust, red dust of Mars. Yet, early in its history, Earth might have looked more like those worlds in some ways. The young Earth's atmosphere had no oxygen and was rich in carbon dioxide and methane. The surface was largely molten at first and heavily bombarded by asteroids, pockmarking it like Mercury. But Earth cooled, oceans formed, life arose, and life's presence terraformed the planet into the benign paradise we now cherish. Earth's geology and biology are deeply intertwined. It is the only planet known where rocks breathe and living creatures move mountains. While Earth has its share of extreme environments, from Antarctica's icy wastes to the Sahara's furnace sands, it remains the gentlest of the inner planets, blessed with liquid water and a breathable sky. It is, simply put, home. And as we study the other planets, we constantly hold Earth as the reference, asking, why is this planet dead or boiling while Earth thrives? The answers inform our understanding of climate, habitability, and the delicate balance that makes our world livable. Stepping away from Earth, we venture back into harsher realms. Mars, the fourth planet from the Sun, has long captured human imagination as a possible abode of life, or at least as a world most similar to our own. It is often called the Red Planet for its reddish-orange hue when seen in the sky, a color due to iron oxide dust coating much of its surface. Mars is about half Earth's diameter and only 1/10 its mass, a modest world that has undergone dramatic change over time. Today, Mars is a cold, dry desert planet. Its atmosphere is a thin envelope of carbon dioxide at less than 1% the pressure of Earth's, essentially a tenuous sky that offers little insulation or protection. Daytime temperatures on Mars near the equator in summer might rise to a balmy 20 degrees Celsius, but at night they plummet far below freezing. At the poles in winter, carbon dioxide from the air freezes directly onto the surface as dry ice, forming seasonal polar caps that sublimate when spring returns. This leads to large seasonal pressure swings and even causes the atmosphere to shift mass between hemispheres, driving global winds. Mars wasn't always so barren. Ancient Mars was more Earth-like. All the evidence we've gathered from orbiters, landers, and rovers tells us that billions of years ago, Mars had liquid water flowing on its surface. NASA's rovers have driven through dry riverbeds and studied layered rocks that formed in long, vanished lakes. We have seen branching valley networks etched into the highlands, immense outflow channels gouged by catastrophic floods, and mineral deposits that only form in the presence of water. Mars today has water too, but it's mostly locked up as ice in the polar caps or underground, and a tiny amount as vapor in the atmosphere. What happened? Mars's grip on its atmosphere weakened over time. Being smaller, Mars lost heat faster than Earth. Its once molten core partially solidified, and the global magnetic field that might have existed early on dwindled away. Without a strong magnetosphere, the solar wind gradually stripped off the atmosphere. Air pressure fell, temperatures dropped, and surface water either froze or escaped into space. Volcanoes on Mars likely vented gas and lava for a time, perhaps providing temporary warmth, but volcanic activity too has waned. The youngest lava flows on Mars are tens of millions of years old, and no eruptions have been observed in modern times. Still, Mars is not entirely static. It has weather. Thin as it is, the atmosphere can stir up winds that raise reddish dust into towering dust devils that dance across the plains, and occasionally into planet-wide dust storms that can shroud the entire globe in haze for weeks. Its sky often has a butterscotch hue due to fine dust suspended in the air. Wispy clouds of water ice occasionally appear, and at dawn and dusk they can catch the sunlight, creating delicate pastel streaks in the Martian sky. Mars also has seasons, similar in cause to Earth's. In spring and summer, the polar CO2 ice caps partially evaporate, exposing underlying water ice. In winter, they grow as CO2 snow falls. On a Martian summer day, you might see frost that formed overnight glinting in the morning sun, or even a hazy, localized dust cloud that could be analogized to a Martian rainstorm of dust. The Martian surface is a study in contrasts. There are immense shield volcanoes on the Tharsis Bulge that dwarf any on Earth. Just off Tharsis lies Valles Marineris, a canyon system so vast it would stretch across the entire United States, up to 4,000 kilometers long, 200 kilometers wide, and 7 kilometers deep. This Grand Canyon of Mars likely started as a tectonic crack when Tharsis uplifted, then was widened by landslides and perhaps erosion. Elsewhere, the northern hemisphere of Mars consists mostly of rolling, lower plains, whereas the southern hemisphere is high, cratered highlands, an indication that something created a dichotomy in Mars's crust ages ago. Scattered across Mars are impact craters of all sizes, some hosting dune fields within them, others showing gullies on their walls that hint at past flows of water or CO2 ice. Unlike the Moon or Mercury, however, Mars's craters often look worn down, softened by wind, blown dust, or perhaps by ice action. There are also curious features, like the mysterious recurring slope lineae, dark streaks on some crater and canyon walls that grow in warm seasons and fade in cold, once thought to be brine flows. Despite its harshness, Mars remains the most potentially habitable planet after Earth. It is cold, but not beyond the tolerance of life. In fact, hardy microbes on Earth survive in Antarctic ice and dry valleys that resemble Mars. It has water ice in abundance, and perhaps liquid water brines occasionally trickling just beneath the surface. In recent years, tantalizing detections of methane in Mars's atmosphere have stirred excitement, since methane can be a byproduct of microbial life. The dream of life on Mars is one of the reasons we have sent so many probes there. From the Viking landers in the 1970s to the latest Perseverance rover drilling samples for a future return to Earth, we have been reading Mars's history like a book written in rock. That story appears to include a long, gone epoch of rivers and lakes, a gradual climate catastrophe, and the transformation into the cold desert we see now. Mars today is a time capsule of planetary evolution, showing us what can happen when a world's fortunes turn for the worse. Its once thick atmosphere is mostly gone. Some of it lies frozen at the poles, some in the ground, and some atoms still drift in space as a tenuous corona around the planet. In some, the inner solar system presents 4 different fates for terrestrial planets. Mercury is an airless, baked rock, a planet stripped to its core. Venus is a suffocating hothouse under perpetual clouds, a planet where the greenhouse effect ran rampant. Earth is a balanced, vibrant world, a planet just right for liquid water and life. Mars is a once potential Earth that fell into cold desolation, a planet that lost its warmth and air. These worlds teach us about volcanism, climate, and habitability by comparison. Why did only Earth end up with lush oceans and a breathable sky? The inner planets hold the clues in their craters, rocks, and atmospheres. As we leave Mars and venture beyond the asteroid belt, the sunlight fades and an entirely different kind of planet emerges. Titanic worlds of gas and ice, where swirling storms could swallow continents and rings of dust and ice trace cosmic harmonies. Let us now step into the realm of the giant planets, where extremes reach a new level and moons become worlds of their own. Giants of the outer solar system: Jupiter, Saturn, Uranus, Neptune. Passing beyond the asteroid belt, the sun's warmth diminishes and the worlds undergo a dramatic change. Here lie the giant planets, titans composed mostly of gas and icy fluids, with no solid surface to stand on. They dwarf the rocky inner planets in size and mass. Each is like a miniature solar system unto itself, with rings and moons forming complex families. They are planets of colossal storms, deep mysteries, and delicate rings, where the simple word surface loses its usual meaning. Jupiter is the colossus of our solar system, the fifth planet from the Sun, and by far the largest. With a diameter of about 143,000 kilometers and a mass more than twice that of all the other planets combined, Jupiter looms as a great banded sphere of tan, orange, and white. Composed mostly of hydrogen and helium gas, it is often likened to a failed star. It would have needed to be about 80 times more massive to ignite fusion in its core. Instead, Jupiter shines not by its own light, but by reflecting the sun's, and by emitting a bit of heat it retains from its formation. When you gaze at Jupiter through a telescope, you see not a solid surface, but the tops of its cloud decks, organized into parallel bands that wrap around the planet's fast rotating body. Jupiter spins on its axis in just under 10 hours, an incredibly fast rotation for such a huge planet. This rapid spin flattens Jupiter slightly and drives strong jet streams that separate its cloud bands. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a titanic storm roughly 1.3 times the width of Earth that has raged for centuries like a cosmic hurricane. Its brick red clouds swirl counterclockwise in Jupiter's southern hemisphere. Though it has been shrinking in recent decades, the red spot remains an icon of planetary science, a reminder that weather on other worlds can be on a scale far beyond anything on Earth. Jupiter's entire atmosphere is dynamic. Smaller storms come and go, white ovals and brown barges drift in the cloud lanes, and lightning crackles within towering thunderheads the size of continents. Near the poles, Jupiter's Juno spacecraft has revealed clusters of cyclones arranged in geometric patterns. At the North Pole, a central cyclone is encircled by 8 others like a flower of storms, all enduring and maintaining a surprisingly stable configuration. At the cloud tops, the temperature is around 45 degrees, but it grows hotter and denser as you descend. There is likely no sharp surface where gas turns to liquid. Rather, as pressure increases, hydrogen gas gradually becomes a supercritical fluid, and then a weird metallic form in Jupiter's depths. Beneath the storms, Jupiter hides more wonders. Its immense gravity compresses its interior to extreme pressures. Deep down, the hydrogen is squeezed into a state where it conducts electricity like a metal. This metallic hydrogen region, rotating rapidly, is believed to generate Jupiter's powerful magnetic field, the strongest of any planet, with a magnetosphere that extends millions of kilometers and envelops Jupiter's moons. This magnetic field traps charged particles and produces intense radiation belts. It also powers brilliant auroras at Jupiter's poles, glowing in ultraviolet and infrared, far larger and more energetic than Earth's. The interplay of Io's volcanoes and Jupiter's magnetosphere even creates a permanent flow of electric current between them and fills Jupiter's environment with sulfur and oxygen ions that contribute to auroras and radio bursts. Surrounding Jupiter is a retinue of moons, more than 90 known at last count, ranging from tiny asteroid-like rocks to planet-sized spheres. The four largest, the Galilean moons, were first seen by Galileo in 1610 and remain some of the most remarkable places in the solar system. Closest to Jupiter orbits Io, a tortured volcanic world. Io is the most volcanically active body in the solar system. Its interior flexed and heated by Jupiter's gravity. Its surface is mottled with sulfurous yellows and oranges and dotted with erupting volcanoes that spew fountains of lava and giant plumes of sulfurous gas that can rise 300 kilometers high. Next out is Europa, a smooth, icy moon slightly smaller than Earth's moon. Europa's surface is crisscrossed with reddish-brown cracks and ridges over a bright white shell of water ice. Almost no craters mar Europa. It's young and active. Beneath that ice, scientists are confident lies a global ocean of liquid water, kept fluid by tidal heating. Europa's hidden ocean, perhaps 100 kilometers deep under an ice crust a few to 30 kilometers thick, makes it one of the prime candidates in the search for extraterrestrial life. Beyond Europa comes Ganymede, the largest moon in the solar system. Ganymede is a frozen world with a mix of old, dark, cratered regions and somewhat younger, lighter grooved terrain from past tectonic activity. It even has its own internally generated magnetic field, the only moon known to have one, hinting at a molten iron core within. And then Callisto, the outermost Galilean moon, an ancient cratered ball of ice and rock that appears to have changed little in 4 billion years. Callisto's surface is saturated with impact scars, a record of the early solar system's heavy bombardment. While not as flashy as Io or Europa, even quiet Callisto might harbor a subsurface ocean, and it has a composition like a primordial mix of rock and ice, a relic of the solar nebula. Each of these moons could warrant chapters of their own, and indeed they will come up again when we talk about habitability and exploration. For now, they underscore Jupiter's role as a mini solar system, a master planet with its own complex gravitational web, shaping the lives of its moons. Jupiter also sports a barely visible ring system, thin bands of dust encircling the planet above its cloud tops. Unlike Saturn's bright icy rings, Jupiter's rings are tenuous and were discovered only when Voyager 1 flew through Jupiter's shadow and saw them glint. The dust likely comes from meteoroid impacts on small inner moons. The rings remind us that all giant planets have rings of one form or another, a natural consequence of having many orbiting bodies and frequent collisions or ice eruptions to supply ring material. Now we move one step farther out to Saturn, the sixth planet from the Sun, often considered the most beautiful. Saturn is a gas giant like Jupiter, but slightly smaller and significantly less massive. In fact, Saturn has the lowest density of any planet, less than water, meaning if you could find a bathtub big enough, Saturn would float. Visually, Saturn is stunning for one reason above all: its rings. Saturn's rings form a broad, flat disk encircling the planet's equator, composed of countless icy particles ranging in size from dust grains to boulders. They sparkle in the sunlight and are divided into several major rings separated by gaps. From Earth, even a small telescope shows Saturn's rings as a separate structure. Up close, they resolve into myriad ringlets, ripples, and braids sculpted by gravitational interactions with Saturn's moons. The rings are extremely thin, only tens of meters thick in most places, despite spanning over 250,000 kilometers in diameter. They are likely relatively young and are slowly evolving. Saturn's gravity is pulling ring material inward, which means the rings may gradually thin out over tens of millions of years. For now, however, they are a breathtaking demonstration of cosmic geometry and physics. A disk of ice grains tracing the invisible lines of Saturn's gravity and rotational balance. Saturn itself, beneath the rings, is often seen as a pale golden globe banded by subtle belts and zones like Jupiter's, but far more muted in color. Its upper clouds are composed of ammonia crystals. Deeper down likely lie clouds of ammonium hydrosulfide and water, but these are hidden beneath hazes. Saturn's atmosphere is colder than Jupiter's, and its weather, while not as vividly colored, can still be violent. Roughly once per Saturnian year, Saturn experiences a great white spot, an enormous storm that erupts and encircles the planet. One such storm was observed by Cassini in 2011. It began as a brilliant white cloud in the northern mid-latitudes and spread into a band that wrapped around Saturn, accompanied by lightning and turbulent swirls the size of Earth, before dissipating. Saturn also exhibits a bizarre phenomenon at its north pole, a long-lived hexagonal jet stream pattern, first noticed by Voyager and later seen in detail by Cassini. This six-sided wave, like flow of clouds, each side longer than Earth's diameter, rotates as a unit around the pole. At the center of the hexagon sits a whirling hurricane, like vortex with an eye several thousand kilometers across. Why Saturn's atmosphere naturally forms a hexagon is still debated. Likely it's a result of a standing wave in the fluid dynamics of its atmosphere at that latitude. Like Jupiter, Saturn radiates more heat than it receives from the Sun, though the mechanism is different. Saturn appears to be undergoing helium rain as the planet cools. Helium condenses out of the hydrogen, helium mixture in the upper layers and falls inward, releasing gravitational energy as heat. This helps drive Saturn's weather from below. Saturn's magnetic field is strong. Uniquely, Saturn's magnetic field is almost perfectly aligned with its rotation axis, a fact that challenges dynamo theories. Nevertheless, Saturn has bright auroras observed at ultraviolet wavelengths, and its strong field traps some radiation. Saturn's family of moons is rich and varied, more than 80 known moons. The largest, Titan, is one of the most intriguing objects in the solar system. Titan is bigger than Mercury and enveloped in a thick orange haze of atmosphere. In fact, Titan is the second largest moon and the only moon with a substantial atmosphere, even denser at the surface than Earth's, composed mainly of nitrogen with a few % methane. For a long time, that smog hid Titan's surface completely. But the Cassini mission's radar and the Huygens lander unveiled a world surprisingly Earth-like in some ways. Titan has rivers, lakes and rain, but of liquid methane and ethane instead of water. At Titan's frigid surface temperature of 179 degrees, water is as hard as rock, and hydrocarbons take the role of the water cycle. Dark methane seas dot Titan's polar regions, complete with shoreline features, islands, and possibly waves. There are branching river channels carved by methane rain flowing into valley networks, and extensive equatorial dune fields made of exotic organic sand. Standing on Titan, you would see an orange-colored sky and a dim sun. The air pressure is about 1.5 times Earth's. You could almost fly by flapping wings strapped to your arms, given Titan's dense air and low gravity. It is an alien yet eerily familiar landscape. In fact, perhaps the most Earth-like place in the solar system, aside from Earth itself, albeit at cryogenic temperature and with a completely different chemistry. Titan likely has a subsurface water ocean as well, beneath the ice crust, making it a double world of interest. A possible haven for some form of life in the warm water below, and a laboratory for prebiotic chemistry in the organic, rich surface environment. Another of Saturn's moons has seized our attention, Enceladus, a small ice moon only about 500 kilometers across. Enceladus looks like a shiny white snowball, reflecting almost all sunlight. For years, its smooth, bright surface hinted something was renewing it. The Cassini spacecraft confirmed that in spectacular fashion. It discovered active water geysers erupting from Enceladus's south pole. Dozens of icy jets spray water vapor and tiny ice particles continuously into space. feeding Saturn's faint E-ring and indicating a subsurface ocean of liquid water beneath Enceladus's fractured crust. Cassini even flew through the plumes and detected salts, organics, and tiny grains of silica. In other words, Enceladus has nearly all the ingredients for life: water, heat, and organic molecules. And it's ejecting them into space, begging for further exploration. The surface around the South Pole has tiger-stripe fissures that are warm and flexing with tidal pulls from Saturn, essentially cryovolcanic vents. This little moon, with a global ocean about 30 kilometers below an ice shell some 20 kilometers thick, has become one of the prime targets in the search for extraterrestrial life. Saturn's other moons offer delights as well. Iapetus, half of its surface bright as snow and the other half dark as coal, with a unique equatorial ridge that makes it look like a walnut. Rhea, Tethys, and Dione, medium-sized moons, heavily cratered and cut by ancient canyons. Dione might hide a subsurface ocean too. Mimas, with its giant crater, Herschel giving it a Death Star appearance. Phoebe, a retrograde irregular moon perhaps captured from the outer solar system, rich in primitive material. Each moon tells a different chapter of Saturn's story, from formation to capture to geologic evolution. Yet, through it all, Saturn's majestic rings cast their shimmering veil, illuminating the night sides of moons and casting shadows that stripe Saturn's own cloud tops in eclipse season. Beyond Saturn, the sunlight becomes faint. We reach the ice giants, Uranus and Neptune, the seventh and eighth planets. They are called ice giants, not because they are made of solid ice, but because in addition to hydrogen and helium, they contain a higher proportion of ices, water, ammonia, methane, in a hot, slushy, fluid state inside. Uranus orbits about 2.9 billion kilometers from the Sun, taking 84 years to complete one orbit. It's a pale blue-green orb, about 4 times Earth's diameter, and notably tilted over on its side. Uranus's axial tilt is 98 degrees, meaning it practically rolls around the Sun like a ball. This bizarre orientation is likely due to a colossal collision with a protoplanet long ago. The consequence is extreme seasons. Each pole gets 42 years of continuous sunlight, then 42 years of darkness. When Voyager 2 flew by in 1986, it was southern summer, and Uranus's south pole faced the Sun almost directly. Voyager saw a virtually featureless sphere, a smooth cyan disk with only the faintest hints of cloud, bands or spots. Uranus looked like a painted marble, leading many to call it bland. But as Uranus approached its equinox in 2007, Earth-based telescopes and Hubble started seeing signs of weather: bright white cloud caps, dark spots, and streaky clouds. Uranus, it turns out, has a dynamic atmosphere that awakens when the Sun's heating is distributed more evenly. During the 2010s, astronomers observed some storms with ferocity comparable to Neptune's, including one huge storm in 2014 that was surprising given how far from the Sun Uranus is. Most of the time, though, Uranus is tranquil looking, with gentle banding visible in enhanced images, and a serene aquamarine hue due to methane in its atmosphere, absorbing red light and reflecting blue, green. At cloud tops, Uranus is a frigid 215 degrees Celsius. Uranus also comes with rings and moons. It has a set of thin, dark rings made of radiation, darkened ice, and dust. They are narrow, kept in line by shepherd moons, and not nearly as showy as Saturn's, but they form a delicate series of hoops around the sideways planet. Uranus's moons include Titania, Oberon, Ariel, Umbriel, and Miranda. They are icy, cratered worlds, a few showing evidence of past internal activity. Miranda, for instance, displays one of the strangest surfaces in the solar system: patchwork regions of ridges and valleys next to older cratered terrain, and a cliff estimated at 20 kilometers high, a fall from which would take 15 minutes in Miranda's weak gravity. It's as if Miranda was shattered and reassembled, or underwent partial melting that froze in bizarre patterns. The larger moons have lesser quirks. Ariel has relatively few craters and signs of youthful resurfacing. Titania has giant canyons. Uranus's moons, like the planet, roll on their sides as they orbit E, which means, at solstices, one hemisphere of each moon is in continuous sunlight and the other in darkness. What seasonal effects that might cause on those frigid surfaces, we don't really know yet. Neptune, the eighth planet, orbits about 4.5 billion kilometers from the Sun, taking 165 years for one circuit. It's very similar to Uranus in size and composition, but Neptune is notably more active and more intense in color, a deep azure blue. Discovered in 1846 by mathematical prediction, Neptune was visited by Voyager 2 in 1989. Voyager 2 found a dynamic atmosphere, a great dark spot in the southern hemisphere and bright white clouds zipping around. Neptune's winds are the fastest in the solar system, up to 2,100 km/h, especially around those dark oval storms. The great dark spot seen in 1989 was a large high-pressure system exposing darker gases below, roughly the size of Earth, and it vanished a few years later. But other dark spots have since appeared and faded on Neptune. Unlike Jupiter's huge stable spot, Neptune's seem to be shorter, lived storms that come and go every decade or so. Neptune's upper atmosphere is about 200 degrees. Intriguingly, Neptune, like Jupiter and Saturn, radiates about 2.6 times more heat than it gets from the Sun, likely due to residual heat from formation. This internal energy might help drive the vigorous weather we see. Neptune's seasons last over 40 years. We haven't observed a full Neptunian season change yet, but in the decades since 1989 to the 2020s, we've seen some puzzling climate changes. The global temperature in Neptune's stratosphere actually dropped by about 7 degrees Celsius from 2003 to 2018. Then the South Pole suddenly warmed by 11 degrees from 2018 to 2020. It's a reminder that these far-off atmospheres can have variability we don't fully grasp yet. Neptune, too, has rings and moons. It sports faint rings with clumpy arcs. The outer Adam's ring has segments named Liberty, Equality, and Fraternity, where dust is clustered, for reasons initially mysterious until moonlets were found that shepherd those arcs. And Neptune's moon's number 14 at last count. The standout is Triton, Neptune's largest moon, which orbits backward relative to Neptune's rotation. Triton is a captured Kuiper belt object, likely snared by Neptune's gravity long ago. Triton is an ice world almost as big as our moon, with a young surface of frozen nitrogen, water ice, and weird cantaloupe terrain, and it is geologically active. Voyager 2 saw geysers on Triton, dark plumes of nitrogen gas and dust spraying up from the surface, carried by winds before falling. These are essentially cryovolcanoes driven by seasonal heating of Triton's south polar cap. Triton's thin atmosphere is about 1/70,000th Earth's pressure, but enough to have winds that bent those geyser plumes. Triton is extremely cold, yet it still has this slight atmosphere and active geysers, an astounding find. Triton likely has a subsurface ocean as well, kept liquid by residual internal heat or past tidal heating. Because of its retrograde orbit, Triton is slowly spiraling inward toward Neptune. Billions of years from now, it may either break apart into a spectacular ring or crash into Neptune. Neptune's other moons are much smaller and ice, rocky. Nereid has an extremely elongated orbit. Proteus is the second, largest, but still irregularly shaped. It's as large as an object can get without its gravity crushing it into a sphere. Proteus, dark and heavily cratered, might have avoided melting into a sphere by forming late, after the solar system calmed down. Tiny Hydra and Naiad and others zip around Neptune in closer orbits, some in complex resonant dances. Neptune's moon system likely lost whatever original satellites it had during Triton's capture. What we see now are either captured asteroids, comets, or fragments of an ancient moon system reassembled in new orbits. Thus, the outer solar system presents grandeur quite different from the inner. Here we have giant globes of gas and ice, lacking solid surfaces, but adorned with storms larger than Earth and delicate rings. We have an array of moons that are worlds in their own right, some sterile and cratered, others with subsurface oceans or thick atmospheres or erupting geysers. The giant planets act as architects and guardians of the solar system. Their gravity shaped the orbits of countless smaller bodies and may have steered water-rich comets toward the inner planets, possibly delivering Earth's oceans. Jupiter, especially, has shielded the inner solar system at times by vacuuming up comets, though it can also fling asteroids our way if they get too close. The giants likely migrated early on, scattering the debris disk and causing the late heavy bombardment that peppered the inner worlds with craters, and perhaps ejecting leftover planetesimals to form the distant Oort cloud of comets. As we leave Neptune behind, we pass into the realm of icy debris, the Kuiper Belt and beyond, where the sun's influence wanes. Yet even here we find worlds of consequence, the dwarf planets, which challenge how we define planethood and carry clues to the solar system's origin. Dwarf planets, worlds at the edge, and the definition of planethood. Far beyond Neptune's orbit, the solar system continues into a vast realm of icy bodies. Here, in the dim frontier, lies the Kuiper Belt, a broad ring of frozen remnants from the solar system's formation. Among these are several worlds large enough to be round, worlds that in another context might have been called planets. In fact, one of them was long honored as the 9th planet, Pluto. Today, we classify Pluto and similar bodies as dwarf planets, a category born from the realization that our cosmic neighborhood has more planets than we once thought, and that not all planets are equal in their orbital status. These distant dwarfs are small in size but rich in diversity, and they have forced us to confront the question, what does it truly mean to be a planet? Let us begin with Pluto, the iconic dwarf planet and former 9th planet. Discovered in 1930, Pluto orbits roughly 5.9 billion kilometers from the Sun on average, on a path that is highly inclined and elliptical. For 76 years, it was counted as the outermost planet, depicted as an icy oddball, until the early 21st century brought a paradigm shift. Pluto is about 2,377 kilometers in diameter, less than 20% of Earth's diameter, smaller than our Moon. But what it lacks in size, Pluto makes up for in personality. In 2015, NASA's New Horizons spacecraft flew past Pluto and revealed an astonishingly complex world. Far from a simple cratered ice ball, Pluto displays a mosaic of terrains: towering water, ice mountains rising 4,006 kilometers high, vast smooth plains of nitrogen ice with no craters, and dark reddish regions rich in organic molecules processed by sunlight. The most famous feature is Tombor Regio, nicknamed the heart of Pluto, a bright, heart-shaped area dominating one hemisphere. The left lobe of this heart, Sputnik Planitia, is a 1,000 km wide basin filled with nitrogen, carbon monoxide, and methane ices. This frozen plain is segmented into polygonal cells, evidence of convection. Pluto's interior heat causes the nitrogen ice to slowly overturn like a lava lamp, erasing craters and renewing the surface. It's a bit mind-boggling. Here is a tiny world at the solar system's edge, with active geology powered perhaps by the slow cooling of an internal ocean, or by exotic forms of heat transfer in the ice. Pluto's thin atmosphere is another surprise. When near perihelion, its surface ices sublimate, forming a tenuous atmosphere of nitrogen with a touch of methane. This atmosphere is about 100,000 times thinner than Earth's, but enough to form layers of delicate blue haze, as imaged by New Horizons when it looked back at Pluto, eclipsing the distant Sun. In Pluto's sky, the Sun is just a brilliant star, but it still drives a faint weather cycle. As Pluto recedes from the Sun, its atmosphere can partially freeze out onto the surface. New Horizons saw that Pluto's skies are layered with haze up to 200 kilometers altitude, and that the atmosphere is slowly escaping to space, forming a tail like a comet's. Standing on Pluto, you'd see a dim daylight with a charcoal-colored landscape, low gravity, and if you looked up, a thin bluish glow around the horizon from the atmospheric haze. Pluto doesn't wander alone. It has a system of 5 moons. The largest, Charon, is so big that Pluto and Charon orbit each other around a point in space between them. Charon itself is a fascinating world. New Horizons showed it has a rugged surface with a massive equatorial canyon system far longer and deeper than the Grand Canyon, and a strangely bi-colored complexion. The northern polar region of Charon is reddish, likely stained by gases that escaped Pluto and froze onto Charon, then were altered by solar radiation into reddish tholins. The mutual orbit of Pluto and Charon is tidally locked. Each keeps the same face toward the other, waltzing through space as an inseparable pair. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier and irregularly shaped, probably captured or coalesced debris from the giant impact that created the Pluto-Charon system billions of years ago. Moving outward, we find Eris, the troublemaker that precipitated Pluto's demotion. Eris was discovered in 2005 by a team led by Mike Brown. It's an object currently slightly smaller in diameter than Pluto, but more massive by about 25%. Eris orbits the Sun on a highly eccentric path. When found, Eris was hailed in the media as the 10th planet, but its existence underscored that Pluto was not unique. Astronomers suspected many Pluto-sized objects awaited discovery. Eris was named after the Greek goddess of discord, fitting for the chaos it introduced into our understanding. It has one known moon, Dysnomia. Eris's surface is extremely bright. Its great distance means Eris is in deep freeze. If it comes closer, it might develop a thin atmosphere like Pluto's that refreezes when far out. Eris's discovery forced the IAU to formalize the definition of planet, and under that definition, Eris joined Pluto as a dwarf planet. But in terms of geology and interest, Eris is very much a planet, like world, simply one of a vast collection in the Kuiper belt. Besides Pluto and Eris, the IAU has so far recognized 3 other dwarf planets: Ceres, Haumea, and Makemake. Ceres is unique as the only dwarf planet located in the inner solar system, residing in the asteroid belt between Mars and Jupiter. In fact, Ceres was the first dwarf planet discovered and initially considered a planet until many more asteroids were found. Ceres is about 940 kilometers in diameter, roughly the size of Texas, and contains about a third of the mass of the entire asteroid belt. NASA's Dawn orbiter visited Ceres in 2015 and unveiled a cratered world that, while much smaller than Pluto or Eris, still shows signs of internal complexity. Most famously, Dawn spotted mysterious bright spots on Ceres, particularly in the crater Ocata. These bright patches turned out to be deposits of salts left behind by briny water that erupted or seeped to the surface, essentially cryovolcanic salt flats. This indicates that Ceres, even at its modest size, had a subsurface reservoir of salty water or mud that occasionally breaches the surface as a kind of ice volcano. One such cryovolcano on Ceres is Ahuna Mons, a solitary mountain likely formed by the extrusion of viscous, icy material that then hardened. Ceres likely differentiated into a rocky core and icy mantle. It may even hold a remnant subsurface ocean or pockets of liquid. Though cold and airless, Ceres surprises us by being a kind of geological bridge between the rocky inner worlds and the icy outer worlds. Back to the Kuiper belt, Makemake is another dwarf planet, slightly smaller than Pluto. Discovered in 2005, Makemake orbits at about 45 AU on a mildly tilted orbit. It has a very high reflectivity as well, with a surface of methane and ethane ices that give it a red-brown color. For a long time, Makemake was thought moonless, but in 2016, a tiny moon was found in Hubble images. Knowing its moon will allow us to determine Makemake's mass and density. Makemake has no known atmosphere, and its average surface temperature is around 240 degrees Celsius. Then there is Haumea, one of the strangest known dwarf planets. Discovered in 2004 and officially named in 2008 after the Hawaiian goddess of childbirth, Haumea is not spherical but rather ellipsoidal due to its incredibly rapid rotation. A day on Haumea is just under 4 hours. This fast spin elongated Haumea into a rugby ball shape. It's as if someone grabbed a ball of taffy and whirled it around. The centripetal force stretched it out. Haumea is also notable for its composition. It's largely water ice with a denser core, suggesting it might be the fragment of a larger body that collided and spun up. Supporting that, Haumea has 2 moons and is associated with a swarm of smaller Kuiper belt objects that share similar orbits and water-ice spectra, likely pieces of Haumea's shattered past self. In 2017, observers caught Haumea eclipsing a star and discovered it even has a ring, a 70-km wide ring of particles around its equator, likely in the plane of its fast rotation. Haumea's existence stretched our idea of a planet, showing that something can be round-ish and orbiting the Sun, yet far from symmetric or solitary. Beyond these, dozens of other objects around the size threshold for dwarf planet likely exist. Quaoar has a moon and possibly a ring of its own. Sedna lurks on an 11,000-year orbit that takes it out to nearly 1,000 AU, possibly the first known member of the inner Oort cloud. The more we look, the more we find a continuum of worlds bridging planets and comets. The dwarf planets collectively highlight the continuum of planetary sizes and the gradations in the solar system's architecture. They forced the question, where do we draw the line between planet and smaller bodies? The 2006 IAU definition drew that line based on orbital dominance. By that rule, Pluto, Eris, Haumea, Makemake, and Ceres were reclassified because they share their space with many peers, but that definition remains debated. Some planetary scientists prefer a geophysical definition. If it's round by self-gravity, call it a planet, which would make dwarf planets planet in a broader sense. Others note that even Earth hasn't entirely cleared its orbit, but Earth so overwhelmingly outweighs them that the spirit of the definition holds. The public often still refers to Pluto as a planet out of affection. In truth, terms like planet are human categories we impose on nature's spectrum. Whether we call Pluto a planet or not doesn't change Pluto itself, with its glaciers of nitrogen, atmosphere that snows out, and potential subsurface ocean. Pluto defies any notion of being a static asteroid. We've learned that these so-called dwarfs can be just as complex and geologically active as the big planets. They are worlds by any meaningful measure. The classification is mainly about how they fit into the solar system's structure. Pluto hasn't cleared its orbit because it lives in a bustling disk of other icy bodies. That tells us about where and how it formed, but it doesn't diminish its status as a fascinating world. Indeed, studying dwarf planets like Pluto and Ceres has yielded huge insights. Ceres taught us that even small bodies can differentiate and possibly harbor liquid water or mud under the surface. Pluto showed that even in the far frozen reaches, geology goes on. Exotic ices can flow and convect like glaciers, and cryovolcanoes can build mountains. These bodies are time capsules from the solar system's formation and laboratories for processes at the extremes. They and their ilk likely delivered volatiles to the larger planets. And when we consider planets around other stars, many might be more akin to these intermediate worlds than to the 8 major planets we started out with. Having completed our grand tour of the solar system, from the Sun, scorched rocks, to the gas leviathans and distant ice dwarfs, we can step back and summarize. Our solar system contains a family of worlds with a common origin but wildly divergent paths. Some went dry and airless, others drowned in thick atmospheres. Some stayed warm inside, churning and resurfacing. Others went cold and quiet. And around at least one modest star out of billions, one small rocky planet found a perfect balance and became alive. With this perspective, we now venture beyond the solar system to the planets that orbit distant suns. Here, we will apply what we've learned to understand how we detect these alien worlds, what types we've discovered, and what that means for the potential for life in the cosmos. Beyond our solar system, the exoplanet revolution. For thousands of years, humans wondered if the stars in the night sky had their own planets. In the last few decades, we found the answer, a resounding yes. We are living through a revolution in which exoplanets, planets around other stars, have gone from speculation to a catalogue of thousands. This discovery has expanded our concept of what a planet can be and placed our solar system in a galactic context. The first discoveries were surprising. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the first confirmed exoplanets, and they were orbiting a pulsar. These were likely bizarre worlds that survived a supernova or coalesced from its aftermath. Not at all what we expected for the first planets beyond our solar system. Then, in 1995, Michel Mayor and Didier Queloz discovered the first exoplanet around a sun-like star, 51 Pegasi b, a planet at least half the mass of Jupiter, but orbiting so close to its star that its year is only about 4 days. This was a hot Jupiter, a kind of planet unknown in our solar system. It forced us to realize that planetary systems can be very different from ours. Since then, a torrent of discoveries has followed. Astronomers detect exoplanets mainly by two methods: the radial velocity method, which measures the star's subtle wobble due to an orbiting planet's gravity, and the transit method, which measures the slight dimming of a star when a planet crosses in front of it. The Kepler Space Telescope stared at 150,000 stars and measured their brightness precisely, catching thousands of tiny dips that revealed over 2,600 confirmed exoplanets. These planets range from larger than Jupiter gas giants to smaller than Earth worlds. We learned that super-Earths and mini-Neptunes are extremely common, yet our solar system has none of those, implying our setup might be somewhat unusual. We found hot Jupiters, gas giants hugging their stars in scorchingly tight orbits, and hot Neptunes and warm Saturns, and more. We found multi-planet systems packed in close to their stars, some with planets in orbital resonances. We found circumbinary planets, planets orbiting two stars. We found free, floating planets by gravitational micro-lensing, rogue worlds that drift through the galaxy untethered to any star. And we found planets in the habitable zones of their stars, at distances where, if conditions are right, liquid water could exist on a rocky surface. One of the most exciting sets of discoveries was the TRAPPIST system. 7 Earth-sized planets orbiting a dim red dwarf star only 39 light-years away. 3 of these lie in the star's habitable zone. They are all tidally locked and crammed in a space that would fit well within Mercury's orbit. This system provides a tantalizing example of a very different kind of solar system architecture, one where a tiny star can have a retinue of Earth-size worlds potentially capable of retaining atmospheres. What are their surfaces like? Could any have water or life? Future telescopes like the James Webb Space Telescope are actually beginning to probe their atmospheres by analyzing starlight that filters through during transits. Exoplanets have shown us an astounding diversity of types. Hot Jupiters, gas giants orbiting extremely close to their stars. These have atmospheric temperatures of 1,000 pounds and 2,500 excites or more. Their atmospheres are puffed up by heat. Some are losing gas under the stellar radiation. They challenged our formation models. How did such big planets get there? We think they formed farther out and then migrated inward due to interactions with the protoplanetary disk or other planets. They taught us that migration can be a common process. Super-Earths. Planets a bit larger in radius or mass than Earth. Some may be rocky, others may have thick atmospheres. They might actually span a spectrum from big rocky planets to small gas planets. Not having one in our system means we had a gap in our understanding. Now we see they might be one of the most common types in the galaxy. A super-Earth might have higher gravity and retain a thick atmosphere or oceans for billions of years. Could they be even more clement for life than Earth? Or could they all turn into gas dwarfs with puffy atmospheres that make them uninhabitable? We're trying to find out by measuring their densities. Some super-Earths like 55 Cancri E are very dense, whereas others like Kepler 38d appear to have low density. Ice giants and sub-Neptunes. Many systems have planets in the 2 through 4 Earth radii range, akin to scaled down versions of Neptune and Uranus. These might have thick hydrogen, helium atmospheres on a rocky/icy core. Some could be more water-rich. The line between super-Earth and sub-Neptune might be around 1.6 Earth radii. Intriguingly, Kepler data showed a dip in planet frequency around that size, suggesting many planets either have significant gas envelopes or have almost none. This phenomenon, the radius gap, likely reflects how planets either stop growing early and stay rocky or accumulate enough gas to puff up. The borderline worlds might have lost some atmosphere due to stellar radiation, ending up as rocky cores. Gas giants. Plenty of Jupiter, like or Saturn, like exoplanets have been found at various distances, some close, some at Earth, like distances, some far out. A few even orbit at Jupiter, like distances from Sun, like stars, implying their systems might have distant architectures vaguely resembling ours. We found giants in eccentric orbits. Some gas giants orbit binary star systems. We've even directly imaged a few young gas giants at wide separations. Rogue planets. Gravitational microlensing surveys have hinted that there may be numerous free-floating planets, perhaps ejected from forming systems or formed in isolation. Some estimates suggested they could be as numerous as stars or more, though recent data suggests not that common for Jupiter mass ones. Still, it implies planet formation can be a turbulent process, with some worlds flung into the galaxy to wander alone. These would have no sunlight, just faint glow from leftover heat or radioactivity. A larger rogue could retain a thick atmosphere and maybe an internal ocean kept liquid by radiogenic heat or tidal heating from a prior moon, but life on such worlds would be a stretch. Exotic worlds. Some planets are simply weird, like lava worlds such as Corot 7b or Kepler 10b. Rocky planets so close to their stars that their surfaces are likely molten on the day side, with rock vapor atmospheres and mineral clouds that rain pebbles. Or ocean worlds that might be nearly all water by mass, essentially giant versions of Europa or Enceladus that grew larger. There's the idea of carbon planets around stars with different compositions, perhaps worlds where graphite and diamonds are abundant, or surfaces of carbide rock under tar, like skies. There are also puffy planets, gas giants with anomalously large radii for their mass, like WASP 17b, which is about half Jupiter's mass, but 1.7 times its size, and planets orbiting pulsars, or extremely metal, poor stars, or white dwarfs, each situation leading to unusual characteristics. When we compare these exoplanets to our solar system, we see that our system might not be typical in some respects. The absence of a super-Earth in our solar system is a puzzle. Perhaps Jupiter's formation prevented one from coalescing by scattering material. The lack of hot Jupiters in our system is a blessing for us. It appears that giant planets that migrate can disrupt inner systems heavily, whereas ones that stay put allow inner rocky planets to remain. Our relatively circular orbits and spaced-out configuration might not be the most common outcome. Many stars have multiple super-Earths in orbits closer than Mercury's, for example. Yet, among Sun-like stars specifically, some analyses suggest systems with a giant planet at Jupiter, like distance and small inner rocky planets, could be not extremely rare either. We're still trying to figure out how special our arrangement is. The significance of discovering exoplanets is profound. We now know that planet formation is a natural part of star formation. Planets are everywhere. The galaxy likely holds tens of billions of potentially habitable rocky worlds. We've taken the concept of planet from 5 wanderers in the sky to a cosmic norm, and each type of planet we find tests our theories. How do hot Jupiters form? Likely through disk migration or interactions. Why are super-Earths so common? Perhaps many systems form multiple mid-sized cores, which either become super-Earths or mini Neptunes, depending on how much gas they capture and how fast they migrate. What about Earth, like planets? Statistical studies from Kepler suggest perhaps 20–25% of Sun, like stars, have an Earth-size planet in the habitable zone. Around red dwarfs, potentially an even larger fraction have Earth-size planets in the habitable zone, as seen with TRAPPIST and others. However, red dwarfs are volatile. Their flares and long-lived activity might strip or sterilize those planets' atmospheres. The search is now shifting from finding exoplanets to characterizing them, measuring their masses and radii, detecting their atmospheres via spectroscopy, and even directly imaging some. We have detected atmospheric constituents on some exoplanets, sodium in hot Jupiter atmospheres, water vapor on some, even hints of things like titanium oxide, or possibly clouds of silicates or iron. In 2019, water vapor was detected in the atmosphere of a Neptune in its star's habitable zone, raising interest. The ultimate goal is to detect biosignatures, signs of life, in an exoplanet's atmosphere, such as oxygen or methane out of equilibrium, or other peculiar combinations that strongly suggest biology. That will require the next generation of telescopes and perhaps specialized space observatories with coronagraphs or star shades to directly see Earth, like planets next to their bright stars. The types of exoplanets we've discovered inform our quest for life. We've learned that terrestrial planets often come in families. A star might have several, some perhaps larger or smaller than Earth. We've seen that habitable zones around red dwarfs can host multiple tidally locked Earth-size worlds. Whether those can support life is an open question. Tidal locking means one side is always hot, the other cold. But if they have atmospheres or oceans, they could redistribute heat. We also consider how giant planets in a system might affect habitability. A Jupiter analog could help by diverting comets or hinder by destabilizing orbits. Our solar system's giant planets likely had a hand in delivering water, and also in preventing too many super-Earths from forming in the inner regions. In the context of habitability, the solar system offers 3 main candidates for life as we know it: Earth, Mars, and ocean moons. But none besides Earth have confirmed life. So as we look outward, we refine what conditions might be needed. Liquid water, certainly, is high on the list. A source of energy is needed. A stable environment over some billions of years might be necessary for complex life. Planets in the habitable zone of Sun, like stars, might be best situated for that. Red dwarf habitable zone planets get a lot of flares, especially in youth. Could life survive that? Possibly, if under ocean or ground, or protected by a magnetic field and thick atmosphere. We remain cautious but hopeful. The future exploration of exoplanets is accelerating. The James Webb Space Telescope is already peering into some transiting planets' atmospheres with unprecedented detail. Upcoming missions like the Nancy Grace Roman Space Telescope will use microlensing to find rogue planets and cold planets further from stars, and test technologies for direct imaging. Further down the line, proposals for missions like LUVOIR or HABEX specifically aim to directly image Earth like planets around Sun, like stars, and search their spectra for biosignatures. On the ground, extremely large telescopes coming online in the late 2020s will be able to probe smaller exoplanets and perhaps take crude spectra of super-Earth atmospheres. It's conceivable that in the coming decades we might identify a planet where life could exist, or even find hints that it does exist, such as an atmosphere out of chemical equilibrium, strongly suggestive of biological activity. As our gaze extends to the stars, we carry the lessons of our solar system with us. We now know Earth is not alone as a potentially habitable world. There may be billions of Earths in our galaxy, but we also know habitability is fragile. Climate catastrophes like what befell Venus and Mars remind us that a planet's fate can change drastically. Earth has been lucky, but we must keep it that way. Life among the stars, the quest for habitability. When we talk about habitability, we usually mean conditions suitable for liquid water and life as we know it. From our study of planets, we've identified key factors. Distance from star. The concept of the habitable zone is crucial. Not too hot, not too cold for liquid water on the surface. For our Sun, that roughly spans from just beyond Venus's orbit to just beyond Mars's. For smaller, cooler stars, the habitable zone is much closer in. For bigger, hotter stars, it's farther out, but those stars live shorter lives. Atmosphere. A planet needs an atmosphere thick enough to create pressure for liquid water and to circulate heat, but not so thick as to induce a runaway greenhouse. Too thin, and water either freezes or boils away. The composition matters too. CO2 provides warmth, but too much can cook a planet. Some gases can be toxic to life. On Earth, life itself altered the atmosphere, creating the oxygen we breathe, which in turn allowed complex life. Magnetic field. As we discussed, a magnetic field can protect a planet's atmosphere from stellar winds. Earth's field likely helped us maintain our water and air over geologic time. Mars lost its field early, and then its atmosphere eroded away largely. Venus lacks a field, but its atmosphere is so thick that even with losses, it remains dense. Around active stars, a magnetic field could be even more critical to buffer the planet from high-energy radiation and flares. Internal heat and geology. Plate tectonics appears to help regulate climate via the carbon cycle on Earth. Volcanism also releases trapped gases and replenishes the atmosphere. A geologically dead planet might end up like the Moon. No atmosphere, cold interior, and static surface, not hospitable. Mars's waning volcanism might have doomed its climate. Venus's rampant volcanism may have contributed to its runaway greenhouse by belching massive CO2. A balance of geological activity is likely beneficial, enough to drive cycles and field generation, not so much as to create continuous global volcanism that might make a world too volatile for stable ecosystems. Stable climate and star output. A planet needs time for life to evolve. Earth has had liquid water for almost 4 billion years through various climate swings. A star's output can change. Earth's biosphere and geology compensated, keeping the planet habitable. If the changes were more extreme, or Earth's feedbacks weaker, life might have been snuffed out. So habitability is a combination of initial conditions and subsequent luck and balancing feedbacks. When we look at exoplanets, especially those in habitable zones, we assess these factors. Does the planet likely have an atmosphere? What's the star like? We've identified some promising, potentially habitable exoplanets. Proxima Centauri, B. TRAPPIST, E, F, G, as mentioned. Earth-sized, in or near habitable zone around a dim star. Kepler, 452b, around a Sun-like star, often touted as older cousin of Earth, is larger, and the star is 6 billion years old. Interesting if it's rocky, but we're not sure it isn't too massive, having a thick atmosphere. Kepler, 2F and Kepler, 186 if, are smaller planets in their stars' habitable zones, though their stars are a bit cooler than the Sun. Many others have been found by Kepler and TESS that are unconfirmed or with limited information. Ultimately, detecting life is the holy grail. What might be a sign of life? On Earth, the combination of abundant oxygen and methane is a strong biosignature. Seeing both would raise eyebrows. Also, things like the spectral edge of chlorophyll could be a signature if we ever got a direct color spectrum of an exoplanet's surface. Even seasonal changes in atmospheric composition could hint at biology. It's tricky because we have only one example of life's impact on a planet, Earth, and alien life might produce different gases. Also, non-biological processes can sometimes mimic biosignatures. So context is everything. We'd need to understand the planet's star, history, and environment to interpret signals, while the exoplanet hunt proceeds mostly via remote sensing. In our own solar system, we can go to these worlds to search for life or conditions. Mars is currently being combed by rovers and orbiters. Europa and Enceladus are top targets. Europa Clipper will orbit Jupiter and repeatedly fly by Europa to map its ice and composition, even scouting for plumes to sample for organic molecules. JUICE will explore Jupiter's moons and eventually orbit Ganymede, studying its ocean and magnetic field. For Enceladus, a future mission concept aims to directly sample its geysers for biomolecules and maybe even signs of microbial life. Titan will be visited by Dragonfly, a flying drone like Lander that will hop across Titan's dunescapes to drill into organics and look for prebiotic chemistry or even life's handiwork. Thus, our exploration strategy is twofold. Within our solar system, investigate all potentially habitable niches. Beyond our solar system, improve our telescopes to identify promising Earth, like planets around nearby stars, and eventually directly image them. We stand at a moment in history where we can, for the first time, meaningfully search for life beyond Earth. Not long ago, planets around other stars was still hypothetical. Now it's routine science. The next leap, finding evidence of life's effects on another world, would be profound. It would tell us whether life is a cosmic common occurrence or a rare fluke. Either answer is deeply significant. If common, the universe may be teeming with biology and perhaps intelligence. If rare, then our pale blue dot is an even more precious oasis in a vast, perhaps mostly sterile desert. Future frontiers, exploring new worlds, and the fate of our planetary journey. What does the future hold for planet exploration? Both in continuing to explore our solar system and in reaching for others, the coming decades promise to be exciting. Within the solar system, several ambitious missions are on the horizon or in progress. We mentioned Europa Clipper and Dragonfly. These will illuminate the potential habitability of ocean worlds. Mars exploration continues. After Perseverance collects samples, a multi-part Mars sample return mission by NASA ESA aims to bring those samples to Earth by the mid-2030s, allowing labs on Earth to scrutinize Martian soil for signs of ancient life with far greater precision than any rover could. Plans for human missions to Mars loom on the multi-decade timescale. The 2030s or 2040s may see the first footsteps on Mars, fulfilling a dream long imagined. Humans could conduct science on Mars that robots struggle with, though robots will likely have already answered the life question by then. At Jupiter and Saturn, the next generation might be missions to actually land or sail in the oceans of the moons. A concept being studied is a Europa lander to drill through a thinner part of the ice, or a penetrator that melts its way down. Even more fanciful is a submarine for Titan's methane seas or an Enceladus ice drilling lander. These are technologically challenging, but so was landing humans on the moon. It's a matter of will and priority. There's also renewed interest in Venus. After decades focusing on Mars, NASA and ESA have recently approved missions to Venus in the 2030s, Da Vinci Plus and Veritas. ESA's Envision orbiter is planned as well. These missions will give Venus a fresh look, important for understanding how Earth, like planets, diverge. If Venus was once more temperate, when and how did it turn so hostile? We might find clues of past water or ongoing volcanic gases. Farther out, Uranus and Neptune remain the only major planets not revisited since Voyager. The US Planetary Science Decadal Survey has prioritized a Uranus orbiter and probe mission for the 2030s. This mission would journey for around 15 years to Uranus, deploy an atmospheric entry probe to sample Uranus's air directly, and orbit Uranus for a few years to study its rings, magnetosphere, and moons. Such a mission would be a bonanza of science. Understanding ice giants will fill a gap in our knowledge of planet formation. After Uranus, Neptune is a logical next target, potentially in the 2040s, possibly with a Triton lander or ocean finder included. These missions, though far off, underscore humanity's commitment to exploring all corners of our solar neighborhood. In the realm of exoplanets, as discussed, new space telescopes like JWST are opening windows. JWST has already begun examining atmospheres of some transiting exoplanets and even directly imaged a couple of gas giants. Over its lifetime, it might be able to probe some super-Earth atmospheres around nearer stars for molecules like water or CO2. The Roman telescope will find many cold exoplanets via microlensing and carry a technology demonstrator coronagraph to directly image a handful of known giant exoplanets, sharpening our skills. By the 2030s or 2040s, we hope to launch a large segmented mirror telescope. Such a telescope, armed with a coronagraph or a starshade, could directly see Earth-sized planets around perhaps dozens of nearby sun, like stars, and take spectra of them, searching for biosignature gases. Imagine seeing a pale blue dot in the sky of another star and detecting, say, oxygen, or even a color variation due to continents and oceans. That would be a civilization, changing discovery. We stand perhaps a generation away from that possibility. There are also imaginative projects like Breakthrough Starshot, which envisions sending gram-sized microprobes to Alpha Centauri using powerful laser sails, reaching 20% the speed of light to get there in about 20 years. While highly experimental, if such technology matured, we could potentially have flyby images of planets around the nearest stars within our lifetimes, perhaps revealing continents or clouds on an alien Earth. It sounds like sci-fi, but no more so than Jules Verne's moon rockets did in the 1860s. Human curiosity drives innovation, and the payoff, touching another star system, would be historic. As we explore, we also reflect. All these worlds we've visited in our minds, from Mercury's battered ground to Neptune's windy blues, have taught us about diversity and commonality. Diversity in that each planet is its own world with unique quirks. Commonality in that they are all part of one grand physical system, obeying the same gravity and chemistry, following similar stages of formation and evolution with variations on the theme. We've seen parallels, volcanoes on Earth and Io, sand dunes on Mars and Titan, polar lights on Earth and Jupiter, ice crusts on Europa and our own Arctic Ocean. We've seen cautionary tales, a planet almost our twin that became a furnace, a small world that lost its shield and dried out. We look back at Earth with new appreciation for its perfectly tuned conditions, not too hot like Venus, not too cold like early Mars, big enough to hold air, spinning fast enough to have a magnetic field, blanketed by life that in turn helps maintain stability. The study of planets has also put us in our place. Copernicus removed Earth from the center. Galileo showed Earth is just one of many bodies. The last century revealed that even the sun is one of billions, and now that planets abound everywhere, our home is just one island in a vast archipelago of worlds. And yet, to us, it's special, the only known cradle of life. As we search for life elsewhere, we can't help but wonder about the rarity or ubiquity of life. Will we find biosignatures on Mars or Enceladus or an exoplanet? If we do, it means life might sprout wherever conditions allow, implying a living cosmos with many neighbors. If we don't, it could mean life is a freak accident, a cosmic miracle unique to Earth. In that case, the responsibility on us as stewards of the only garden of life increases immeasurably. Either way, studying planets has given us a cosmic perspective. Carl Sagan's famous pale blue dot speech encapsulated it. All of human history played out on a mote of dust suspended in a sunbeam. Every planet we visit reminds us of the fragility of habitability, how thin an atmosphere is, how delicate a balanced climate can be. We see Venus and fear a runaway greenhouse. We see Mars and fear the loss of a magnetic field and atmosphere. We turn those lessons to our own situation, recognizing our planet's climate is not static, that pumping greenhouse gases can push Earth toward a new, possibly unfavorable state. The barren surfaces of Venus and Mars urge us to be careful lest Earth follow their paths in some distant future by our own doing. Planets also teach resilience and change. Earth has gone through mass extinctions and recovered. Life has a tenacity. Who knows, maybe life exists in some form under the ice of Europa or in Titan's chemical stew, very different from Earth's biology. If we find even a second Genesis in our solar system, it means life is a cosmic imperative. If we don't find it nearby, we'll keep looking outward. Ultimately, the exploration of planets is a human story of curiosity, wonder, and reflection. We have gone from gazing at wandering stars to sending robot emissaries across the void to stand on those worlds and report back. With each step, we've been awed. We felt the volcanic heat of Io and shivered in the methane rain of Titan. We marveled at Saturn's rings, countless icy particles orchestrated by gravity into one of nature's most gorgeous sights. We flew through a geyser on Enceladus and tasted primordial water. We watched a sunset on Mars through the eyes of rovers, its sky tinged butterscotch by fine dust. These experiences, albeit through our mechanical proxies, have enriched our soul and expanded our imagination of what worlds are out there. Looking up at the night sky now, we no longer see just pinpoints of light. We see other suns with their own planets, perhaps a giant with storms bigger than Earth, or a warm ocean world enveloped in clouds, or a rocky orb struggling to hold on to an atmosphere. We might even see lights of another civilization, though none have been detected yet. The possibility is there, made real by the sheer number of planets. So we end our journey where we began, under the stars. But now, when we point out the wanderers, our neighboring planets, we do so with understanding and kinship. The word planet means wanderer, but ironically, planets also taught us how connected everything is. Wanderers though they are, they orbit in a family, influencing each other and their star. And we, wanderers ourselves, have begun to venture from our home to visit them, first with our eyes, then with our ships, someday perhaps in person. The story of planets is the story of cosmic islands and the voyages between them. It's a tale of creation, how dust can clump and ignite and then leave residue that becomes worlds both barren and lush. It's a tale of destruction and renewal, giant impacts that can destroy worlds or birth moons, atmospheres that can collapse or run wild, but also life that can emerge and transform a whole planet. It's a story that forces us to ask, how common is a world like ours? How rare are we? And where do we go from here? In the next decades, we may finally get an answer to, are we alone? By detecting life signs elsewhere. Or we may find that Earth is singular so far. In either case, planet exploration will continue, driven by the deepest human urges to know and to go. Unmanned or manned, we will likely set foot on Mars, dive into the seas of Europa with submersibles, maybe float in the atmosphere of Titan or Venus in balloons. We will refine our techniques to image Earth like exoplanets. Perhaps one day, far in the future, our descendants will build starships to visit neighboring systems, turning those points of light into landscapes beneath their boots. As our perspective broadens, our appreciation of Earth deepens. The pale blue dot that Sagan spoke of is our only home in a vast cosmos, at least for now. The other planets show starkly that Earth's hospitality is unique in our solar system. So exploring other planets is not just about them, but also about us, holding a mirror to Earth. We see what happens when greenhouse gases go unchecked, or when a small planet cools and dries, or how a protective magnetic field can preserve a world. These lessons are invaluable as we manage Earth's future. Finally, there is an almost spiritual aspect. By understanding planets, we come to understand our place in the universe. No longer are we the center, we are part of something vast and magnificent. The diversity of worlds out there suggests that if life could arise here, it could arise elsewhere. And if it hasn't elsewhere, then we carry an enormous responsibility as the sole known bearers of consciousness to care for our oasis and perhaps spread life beyond it. We began this journey with the ancient wanderers in the sky. Now, having explored the fire of the inner planets, the grandeur of the giants, the ice of the dwarfs, and even peered to the worlds of other stars, we end with a renewed sense of wonder. The night sky will never look the same. Each dot is a sun, many with planets, some perhaps with beings looking back at a tiny sun pinprick that is our home. The voyage of planetary exploration has really just begun. There are new horizons to reach, literally, as with the probe New Horizons at Pluto, and profound questions still to answer. But one thing is certain, our curiosity will not cease. We will continue to wander, in person or by proxy, mind and body, outward to the planets and beyond. For in seeking these other worlds, we ultimately seek to know ourselves and our place in the cosmos. It is a grand story, one that spans from the fires of creation to the potential spark of life, and it's a story with no end in sight. Each planet we visited, by telescope or spacecraft, has left us changed. They have shown us beauty beyond measure, forces beyond fear, and resilience beyond expectation. In their extremes we find meaning. Mercury's day, night cycle, whispering that too much heat and too little air yields desolation. Venus's clouds warning how quickly paradise can be lost. Mars's dry rivers reminding that climate can turn on a planet. Jupiter's storms humbling us with their power. Saturn's rings teaching the elegance of gravity's order. Uranus and Neptune revealing that even on the edge of darkness, winds still dance. Pluto and its kin proving that even small worlds can be geologically alive. As we continue to learn, we should also take a moment to feel the awe. We are fortunate to live in a time when the long-lost siblings of Earth have been revealed in all their glory. A human from just 100 years ago could only dream of what we've seen. And a human 100 years from now might walk on Mars or float in a Europa submersible, living our present dreams. Our quest for knowledge and exploration binds the generations in a common continuum of discovery. So, step outside on a clear night. Find Venus blazing in the west or Jupiter rising in the east. Know that you're looking at entire worlds, places that we've now touched with our robotic emissaries and, one day, might touch with our hands. The sky that was once the realm of gods and myth is now open to us as a realm of nature to explore. The wanderers are no longer distant mysteries. They are destinations. They have become real places with landscapes and weather and histories we can narrate. And in exploring them, we've woven their stories into our own. We too are wanderers. As Sagan said, we began as wanderers, and we are wanderers still. We have lingered long on the shores of the cosmic ocean, but now we are setting sail among the stars. In the end, the study of planets teaches us humility and unity. All those worlds out there, and here we are, one small crew on spaceship Earth, sailing together through space and time. The pale lights of Mercury, Venus, Mars, Jupiter, and Saturn in our sky are like signposts, telling us where we've been and where we will go. When we finally decipher the secrets of alien atmospheres or find microbes on a distant moon, it will underscore that we are a part of this universe, connected to the planets and stars around us. We are not apart from nature. We are born of the same processes that birthed the planets. The voyage will continue. New rockets, new telescopes, new generations of scientists and explorers will carry the torch. They'll answer questions we haven't thought to ask, and surely encounter surprises we haven't imagined. Planets will continue to fill us with wonder, whether it's weird new exoplanet types or hidden oceans discovered under icy crusts. Each answer will likely raise more questions, as is the way of science. But that is a joy, not a frustration. It means the adventure of discovery is endless. There will always be another horizon, another world to learn from. And as long as humans have eyes to the sky and minds that dream, we will be out there, exploring, moving outward, one world at a time, forging connections across the darkness. In a sense, by exploring the planets, we are the universe exploring itself. Matter that became life, life that became intelligent, now reaching back out to understand the grand mechanism that produced us. Every footprint left on the moon, every photon counted from a distant exoplanet, is the cosmos coming to know itself through us. Our journey through the planets has thus been a journey inward as well, into the nature of who we are and what we may become. When future explorers stand on Mars and look up at a sky with 2 moons, or when a robotic probe sends back the first images from an Earth, like planet light years away, the sense of connection will only grow stronger. We'll realize ever more that we share the universe with all these worlds, and maybe share it with other life. For now, we cherish our pale blue dot while reaching for others. We end our tour back on Earth, gazing up, but with new eyes. The wanderers in the sky are no longer distant gods, but places we know. Siblings in the solar family, each unique, all kin. We have walked among them in our imaginations and through our proxies. Soon, we will with our own feet. The story of planets is ultimately a celebration of human curiosity. We dared to ask ancient lights what they were, and we answered, revealing a universe richer than our ancestors could have believed. Stand under the night sky and feel that connection, tiny though we are. We understand those points of light now. Mercury, Venus, Mars, Jupiter, Saturn. We know them intimately. And far beyond, around myriad stars, countless other planets circle, waiting for our discovery. The wanderers will guide us outward, and wherever we go, we will carry the legacy of understanding forged here at home. In that sense, the journey of exploring planets is a journey of self-discovery for humanity. We set out to find new worlds, and in the process, we found ourselves, one people on one world, learning that the cosmos is full of worlds. It is perhaps the grandest revelation of all. The planets have taught us that the only borders are those we create ourselves. In the cosmos, all worlds share the same sky. The wanderers still move across the heavens as they did for the ancients. But now, when we see them, we greet them as familiar friends, places we've been or soon will go. And as we trace their paths and even send our emissaries to dance among them, we too become wanderers beyond the earth, united in the eternal quest to know the universe and our place within it. The story of planets, our story, continues, onward and outward, under the cosmic sky that we all share. Darkness. No stars, no ground beneath your feet, and perhaps not even the flow of time, just an infinite, motionless night. Imagine a void, with no up or down, no sound or motion. In that profound quiet, before anything begins, we find a fundamental question taking shape. What is the dark, yawning space that stretches out in all directions? Not the stars or planets that speckle it, but the space itself. the black canvas on which all cosmic lights are hung. What is space, when it stands alone, empty of all things?
Since ancient times, people have looked into the night and pondered the void. Many mythologies begin with a great empty darkness from which creation arises, a cosmic egg in a vast sea, or a formless chaos giving birth to the world. In a way, modern science echoes those old intuitions. We too speak of an initial emptiness that blossomed into the universe we know. We usually imagine space as nothingness, a vacant expanse separating the stars. Even scientists once assumed it was merely an empty stage. In the 19th century, many thought an invisible ether must fill the void, a mysterious medium to carry light. But every experiment to detect this ether failed. Light needed no carrier at all. It moved through pure vacuum. Space, it seemed, could be truly nothing. And yet, if you listen closely to the silence, you may sense something more subtle. The void is not truly void. The darkness is not truly nothing. Space is a presence, an invisible fabric that underlies everything. It is quiet and transparent, so easy to ignore. Yet it is real, physical, and dynamic. Space isn't an empty backdrop, but an active, ever-present matrix. It can bend, it can stretch, it can ripple. About a century ago, our picture of space underwent a profound change. Experiments and new ideas revealed that space is not a fixed, unchanging void at all. It can warp and even participate in the cosmic dance. Gravity, we learned, is not a mysterious pull through nothingness, but a bending of space itself by mass. Space and matter interact continuously. Space is like the quiet canvas that holds a painting, or the pause that makes music melodic, an unseen framework that underlies and gives form to everything. Imagine placing a heavy ball on a taut rubber sheet. The sheet stretches and sags under the weight. In much the same way, anything with mass, a planet, a star, a galaxy, presses on the fabric of space. Space curves gently around it. What we feel as gravity is not a pull through emptiness, but the tendency of objects to slide down those curves. The Earth circles the Sun because the Sun dents the space around it, like a large marble sitting on a stretched cloth. Earth is not tethered by invisible strings. It is caught in the Sun's invisible indentation in space-time, moving along a curved path that to us appears as an orbit. In short, mass shapes the geometry of space, and space guides the motion of mass. Even light, which has no mass at all, follows the curves of space. Over 100 years ago, during a total solar eclipse, astronomers noticed that stars appearing near the eclipsed sun were slightly out of place. Their light had bent on its journey to us, detoured by the sun's warped space. It was a dramatic confirmation that space itself, curved by the sun's presence, was guiding the starlight. Today, we regularly use this effect, called gravitational lensing, to observe distant galaxies. A massive cluster of galaxies can act like a cosmic lens, its curved space bending the light of even more distant objects behind it. Sometimes we see a single galaxy smeared into an arc, or even a perfect ring of light encircling a closer galaxy cluster that is acting as the lens. These mirages are the unmistakable signature of space behaving like a gigantic lens, bending and focusing the paths of light. Through these rings and arcs, we see space itself revealing its curvature to our eyes. If space can bend, it can also stretch. Indeed, the fabric of space has been steadily expanding since the primordial beginning of the universe. Distant galaxies are not just flying away through space. The space between us and them is itself growing. Early observers noticed that the light from remote galaxies is shifted toward the red end of the spectrum, as if the wavelengths have been stretched out. The farther a galaxy, the more its light is redshifted. The straightforward explanation is that space itself is expanding, carrying galaxies apart like raisins embedded in rising dough. Over billions of years,
This expansion has enlarged the distances between galaxy clusters immensely. Another useful image is to picture space as the two-dimensional surface of a balloon, with galaxies like ink dots on that surface. As the balloon inflates, the dots move farther apart from each other. No single dot is the center of the expansion. Every dot sees the others receding. Likewise, in our three-dimensional space, every galaxy observes other galaxies rushing away. If we rewind this expansion in our minds, we find that in the distant past, everything was closer together. Galaxies crowd nearer, stars huddle closer. Far enough back, all the matter and light in the universe was crammed into a much smaller volume than today, a state of incredible density and heat. Space itself was compact and blazing with energy. There was a time when the entire young universe was like a hot, glowing fog. Imagine being present in that early inferno. No distinct stars or structures, just a blazing soup of particles and light everywhere you look. An intense white-orange glare filling all of space. As space expanded and thinned out, that searing brilliance faded to a gentler afterglow. Even now, space carries a memory of that fiery beginning. When we point sensitive instruments to the sky, we detect a faint glow of microwaves coming from every direction. This is the afterglow of the primordial fireball, the cosmic microwave background. It is the light from a time about 380,000 years after the Big Bang, when space had cooled enough for atoms to form and for light to travel freely. Since then, those light waves have been stretched by the ongoing expansion of space until they are microwaves, cooled to only a few degrees above absolute zero. Every patch of space is filled with this soft whisper of ancient light. It is almost perfectly uniform and smooth, but has tiny fluctuations, little freckles of slightly warmer and cooler spots, corresponding to minuscule density variations in the early universe. Those slight differences, on the order of only 1 part in 100,000, became the seeds for galaxies and clusters later on. It's as if the walls of the universe still faintly remember their incandescent youth. This ancient light also gives us clues about the overall shape of space. By studying subtle patterns in the microwave background, scientists have learned that on the largest observable scales, space is remarkably flat in its geometry. In a curved universe, those patterns would appear distorted, larger or smaller than expected, much as drawings on a balloon change size when the balloon is inflated. But observations show no such distortion. The angles of those primordial patterns add up just as they would in flat, Euclidean space. For example, in a universe shaped like a 3D sphere, a closed universe, two initially parallel beams of light would eventually converge and meet, and traveling in a straight line long enough could, in theory, loop you around to your starting point, just as an airplane circling the Earth arrives where it began. In a saddle-shaped or open universe, parallel beams would diverge and triangles would have angles summing to less than 180 degrees. But our measurements show nothing of the sort. This suggests that space, as far as we can measure, is not curved into a giant sphere or warped into an endless saddle. Instead, it stretches out in all directions without substantial overall curvature. Space is, to the best of our knowledge, flat and likely unbounded, or so vast that it might as well be infinite. It might extend infinitely, or perhaps it wraps around on a scale so colossal we cannot detect it. But within our cosmic horizon, space behaves like an endless level plane. To achieve such vast flatness and uniformity, the universe likely underwent an extraordinary growth spurt at the very dawn of time. According to the theory of cosmic inflation, a fraction of a second, on the order of 10 over 32 seconds or less, after the Big Bang, space itself expanded at a mind-boggling rate, doubling in size over and over in the blink of an eye. In that brief moment, what had been a microscopic region inflated to astronomical scales. A region smaller than a proton might have stretched to the size of a galaxy in an instant. This rapid stretching would have smoothed out any curvature or clumps, explaining why space now appears so flat and even on large scales. During inflation, tiny random quantum fluctuations, little blips of density in the microscopic early universe, were blown up to enormous sizes. Quantum fluctuations inherent to space itself, magnified to cosmic proportions, became the seeds of future structures. Regions of the young universe that had just slightly more matter or energy became, after inflation, entire huge regions with that slight edge. Those minuscule differences, perhaps only a few parts in 100,000 in density, gave certain patches of space a head start in gravitationally attracting matter. As the universe aged, those patches grew into the first galaxies and clusters. In this way, inflation planted the seeds of cosmic structure. The slight differences from one place to another, once infinitesimal, became the blueprint for all the galaxies, clusters, and voids that would later develop. Space, by expanding so fiercely, essentially cast the dice for the universe's future architecture, turning tiny quantum wrinkles into the grand pattern of stars and galaxies we observe today. When this furious burst of expansion ended, the energy driving it did not simply vanish. It transformed, heating the universe with a burst of radiation and particles. In essence, when inflation stopped, space unleashed its pent-up energy, igniting the hot Big Bang fireball that people often think of as the beginning of the universe. From that point onward, space continued to expand, but at a calmer pace, filled with a blazing plasma that would eventually cool into atoms, gas, stars, and galaxies. The rapid inflationary expansion set the initial conditions, and the slower expansion that followed allowed the cosmos as we know it to emerge. Inflation also opens the door to a startling idea: a multiverse. If the inflationary expansion happened in our region of space, it might have happened, or be still happening, in others. Some theories suggest that inflation never completely stops everywhere. While it ended in our patch, allowing our Big Bang and galaxies to form, in other regions space might still be inflating, or might have ended at a different time. Each of these regions could become its own universe, a bubble with its own galaxies, and perhaps even different physical constants. Our observable universe would then be just one bubble in a limitless foaming sea of universes. We have no way to directly see these other bubbles. They lie beyond any light we could ever receive. But the multiverse concept shows how our conception of space may extend even beyond the bounds of our own universe. Space, in this grand view, is an ever-expanding ocean, spawning countless cosmic islands. Whether this is true or not remains speculative, but it stretches our imagination of what space could be, not just the stage of one universe, but perhaps a prolific generator of many. Over billions of years following inflation, gravity worked on the tiny density variations left in the fabric of expanding space, drawing matter into clouds and clumps that would ignite as the first stars and galaxies. Galaxies pulled together into groups and clusters, and these linked up via filaments of gas and dark matter, forming a vast cosmic web. On the largest scale, the universe looks like a spider web or a sponge, dense clusters of galaxies connected by thread-like filaments, with enormous dark voids in between. Those voids, immense bubbles, millions of light years across, nearly empty of galaxies, are the regions that gravity emptied out as it drew matter into the filaments. In other words, most of the universe's volume consists of these yawning voids, with the galaxies tracing lacy patterns along their boundaries. It's a breathtaking structure, the invisible scaffolding shaped by gravity out of the expanding fabric of space, with over 80% of the volume of the universe contained in those silent voids. The lights of the stars and galaxies stand out like glittering nodes, but it is the darkness between them that dominates by volume. Now picture yourself in the middle of one of those cosmic voids, utterly removed from any galaxy. You are floating in intergalactic darkness, light years from the nearest star. Around you, the darkness is nearly absolute. Perhaps a faint,
ghostly smudge of a distant galaxy is barely visible in one patch of sky, and another dim glow in the opposite direction. But to your unaided eyes, it would mostly be pure black. The nearest substantial galaxy could be tens of millions of light years away, so far that its light is unimaginably feeble. You are, for all practical purposes, alone in a silent, endless night. This is space at its most austere, a volume of the universe almost entirely devoid of matter. And yet, even here, space is not truly empty. A stray hydrogen atom might drift by now and then, or a thin breeze of particles from some far-off galaxy cluster might waft through. You would also be bathed in the ever-present microwave background radiation from the Big Bang, though you wouldn't sense it without instruments. In this void, you can viscerally feel that space is something real, a vast container with you at the center and almost nothing else around. It's a haunting, beautiful solitude. Such voids are the dark wombs of the cosmos, within which the bright filaments of the cosmic web are suspended. Gravity's architecture, the cosmic web of filaments and voids, is heavily influenced by a form of matter we cannot see, dark matter. Decades ago, astronomers measuring the speeds of stars in galaxies discovered a surprise. In galaxies like our Milky Way, the outer stars orbit the center far faster than expected, based on the visible stars and gas alone. They should have been flung off into space, but they remained bound. It was as if an extra unseen mass was providing the gravitational pull to hold them in. Likewise, galaxies in rich clusters move as though there is much more mass present than we can account for with the observed galaxies and hot gas. And when we observe gravitational lensing by a cluster, the bending of light is far stronger than visible matter alone can explain. All of this evidence points to a vast amount of invisible mass enveloping galaxies and clusters. We call this mysterious substance dark matter. It neither emits nor absorbs light, making it effectively invisible to our telescopes. Yet it outweighs ordinary matter by a factor of about 5. Dark matter forms huge halos around galaxies, extending well beyond the visible stars. Every galaxy, including our own, is embedded in a cocoon of this invisible material. Entire galaxy clusters are swathed in massive clouds of dark matter. Its gravity is what helped pull normal matter into the filaments of the cosmic web in the first place. Without dark matter's guiding gravitational pull, the universe's large-scale structure would have formed much more slowly and differently. We cannot see dark matter directly, but we see its imprint. Space curves around it, and galaxies move under its gravitational influence. Through these effects, the hidden scaffolding of dark matter in space becomes perceptible. Space is quietly filled with an unseen mass that shapes the universe profoundly. In the late 20th century came another revelation. The expansion of space is accelerating. After gravity built the cosmic web, one might expect that over time the pull of all those galaxies on each other would slow the expansion of space. And for billions of years, it likely did slow. But to great astonishment, we have found that in the last few billion years, the expansion of the universe has begun to speed up again. Distant galaxies are receding faster and faster as time goes on. Space is expanding not only steadily, but with an ever-increasing pace, as if some mysterious force is pushing it outward. We give the name dark energy to this unknown cause of cosmic acceleration. Unlike dark matter, which adds gravity, dark energy seems to act as a kind of anti-gravity on vast scales, a subtle pressure embedded in the fabric of space that drives it to expand faster. As space grows, more of this repulsive effect appears, since dark energy is thought to be a property of space itself, pushing galaxies apart with increasing strength. Today, dark energy dominates the universe's energy balance. Roughly 70% of the total contents of the cosmos appears to be this shadowy influence, with dark matter making up most of the rest. The ordinary matter, the stars, gas, dust, planets, and us,
accounts for only a few percent. In an ironic twist, the emptiest thing, space, contains the majority of the universe's energy in this form. The silent void has an energetic underpinning that shapes the cosmos. What this means for the far future is profound. As space expands faster and faster, galaxies that are now visible will eventually slip beyond our cosmic horizon, their light stretched and diminished until they vanish from view. In tens or hundreds of billions of years, everything outside our local group of galaxies will have moved out of reach. The universe will appear to whoever remains as an empty void, with only the local galaxies, perhaps merged into one, in view. For example, in about 100 billion years, the galaxies of the Virgo cluster and beyond may be so far that their light never reaches the Milky Way region. After many hundreds of billions more years, even the nearest large galaxy, Andromeda, now destined to collide and merge with our Milky Way long before then, and its remnants would be far beyond detection. The expansion of space will carry all other islands of matter irretrievably away.
What will the cosmos look like then? In that deep future, the observable universe will become dark and empty, with only faint whispers of local starlight remaining. Perhaps an astronomer living in that far future era on some distant world would peer into the sky and see nothing beyond her own galaxy. She might point her telescope outward and find endless blackness in every direction. All other galaxies would have faded beyond reach or redshifted into obscurity. She would have no way of knowing that a vast cosmos full of galaxies had ever existed. The cosmic truth we know today, that space teems with billions of galaxies, would be hidden from her by the relentless expansion of space. That future astronomer might conclude that her galaxy was the entire universe, a tiny island adrift in infinite nothingness.
For us living in the present cosmos, the discovery of dark energy is a humbling reminder that what we once took to be empty nothingness can control the destiny of everything. The silent space between galaxies turns out to hold a secret power that shapes the entire evolution and future of the universe. Space, the quiet stage, has proven to be the hidden protagonist of the cosmic story. Before we return home, let us take an imaginary journey back through the cosmic expanse. Picture yourself out at the edge of a great cluster of galaxies, where hundreds of galaxies shimmer around you like a glittering swarm. Now you begin to travel back toward our own galaxy. As you move, galaxies drift past, scattered in the vast darkness. You glide along one of the filaments of the cosmic web that leads to the Milky Way, passing other island universes along the way. In the distance ahead, a faint band of light comes into view, the combined glow of billions of stars. Our Milky Way, seen from afar as a hazy, spiral disk of light. You approach it, crossing the immense gulf of intergalactic space. Now you plunge into the outskirts of our galaxy, rushing past sparse outer star clusters and the wispy halo of tenuous gas. The star density increases around you as you enter the Milky Way's disk. Entire clusters of young stars drift by. Great nebulae, stellar nurseries, glow softly in pink and blue. By the time you near the inner regions, stars surround you like a sparkling ocean. You weave through a spiral arm, passing magnificent blue-white giants and red supergiants, skirting around clouds of interstellar dust. In the distance, you spot a modest yellow star, our Sun, coming into view. As you draw closer, you see it is accompanied by planets orbiting in the plane of a thin, flat solar system. You sweep past the orbit of Jupiter, then Mars, and now the blue sphere of Earth appears. At this scale, it is a tiny, fragile-looking bead of blue and white, shining against the blackness. You home in on it, watching its oceans and clouds resolve into clarity. In moments, the planet looms large, its atmosphere a glowing thin shell. You slip gently into that atmosphere, experiencing the rush of air as you descend, and finally come to rest on Earth's surface.
back to the soft familiarity of ground beneath your feet. Your fantastical voyage from the end of the universe to our home is complete. Now, having roamed the vast reaches of the cosmos, let us gently return our focus to something more intimate, the space around and within us. We leave the clusters of galaxies and zoom back toward a single galaxy, our Milky Way, and then to a particular star, our Sun, with its family of orbiting planets. Between those worlds stretches millions of kilometers of space, populated only by sparse dust and the thin wind of charged particles from the Sun. Closer in, we see the blue marble of Earth, surrounded by the gauzy blue halo of its atmosphere. From high above, Earth appears as a delicate blue-white sphere hanging in the blackness. Our atmosphere, a thin film of air and cloud, clings to its surface and gradually merges into space. Only a few hundred kilometers up, the air becomes so tenuous that space begins. Beyond that, the sky fades to black. In truth, there is no sharp boundary where space starts. The air just thins more and more until there is effectively none. But effectively, just above the blue sky, the true vacuum of space begins. Only a fragile veil of atmosphere separates us from the cosmic void. There, in low Earth orbit, astronauts aboard space stations witness directly the stark contrast between the bright Earth below and the utter blackness above. They float in microgravity, essentially falling around Earth, immersed in space. When they look up, away from Earth, they see endless darkness spotted with stars that do not twinkle because there is no air up there to flutter their light. The sun shines fiercely without the softening filter of atmosphere, and the divide between day-lit Earth and night-shadowed Earth is a sharp line across the globe. Those astronauts live on the very boundary of space, inside a thin bubble of air in their spacecraft that separates them from the vacuum outside. They often describe the experience as deeply humbling. Above them, an infinite void. Below them, the jewel of Earth with its thin blanket of air. During spacewalks, when they step outside into the vacuum, wearing only a protective suit, they can feel the profound silence and isolation of space. No sound, no breeze, only the distant curve of Earth and the raw, brilliant stars. For them, space is not a theoretical concept, but a palpable reality. They understand in their bones that space is here, around us, an ever-present ocean, just a breath beyond our daily reach. We descend back to the surface now. Picture yourself standing on a quiet night field, looking up at the stars. Although you feel solid ground underfoot and air on your skin, you are as much in space as an astronaut floating in orbit. The space around you is simply filled with a thin mixture of gases, our atmosphere. If you could magically remove all that air, the vacuum that remains would be continuous with the vacuum between the planets and stars. There is no wall or border between space down here and space up there. It is one connected expanse. The same space that stretches between galaxies is present in the room around you, between the walls and among the molecules of air. We truly have never left space. We live at the bottom of a shallow ocean of air, but that ocean is itself embedded in space. People often talk about going into space as if it's somewhere else, but space is already here, step by step. As you climb a mountain or rise in a balloon, the air thins and space reveals itself. Astronauts in orbit are not in a different realm. They have merely ascended above most of the air, into the naked vacuum that was there all along. Space is not distant. It is the backdrop of our existence, even here on Earth. Even our everyday experiences are dialogues with space. Take a breath. You inhale molecules of air that moments ago were scattered across the room, and you exhale molecules that will disperse outward. In doing so, you are stirring the space around you. The air filling your lungs quickly mixes and returns to the atmosphere. ultimately diffusing into the great expanse. In a very real sense, space is the medium through which life interacts with the world. Every movement you make is a displacement in space. Every sound you hear travels to you through vibrating molecules in space. Out in the near-total vacuum beyond Earth's atmosphere, there is no air to carry sound. In space, no one would hear you scream. It is truly silent out there. Every sight you see is brought to your eyes by light crossing space. Space is not an abstract backdrop to life. It is intimately involved in every aspect of our being. Consider even more deeply, you yourself are largely made of space. The atoms in your body are mostly void, their mass concentrated in tiny nuclei, and their size defined by electrons moving through emptiness. If all the empty space in your atoms were somehow removed, you would collapse into a speck far too small to see. And of course, without that space, you wouldn't exist as a living being at all. It is the spacious architecture of your atoms that allows them to bond into molecules, and molecules to build cells, and cells to form a living organism. Thus, space is inside you as much as you are in space. It provides the room that your particles and forces need to operate. We begin to see a pattern from the vast distances between galaxies down to the tiny gaps within atoms. Space is there, quietly doing its work. It provides room for structure to exist, for planets to orbit, for light to travel, for atoms to join and form molecules. The emptiness is not a flaw or an absence. It is an essential ingredient. It allows separation and form. Without the gulf of space within each atom, there could be no distinct atoms and no chemistry, no solid matter as we know it. Without the reaches of space between stars, gravity could not isolate individual worlds where life might arise. Space is the great enabler, the silent canvas that allows matter to take shape and motion to have meaning. Just as a clay pot's usefulness lies in the empty space it encloses, the utility of the cosmos lies in its gaps and hollows. An empty cup holds water. The emptiness within an atom allows it to bond with others. In both cases, what is not there enables what is there to function. And what about space at even smaller scales, far smaller than an atom, smaller than the tiniest subatomic particle? Here we approach deep mysteries. Physicists suspect that if you zoom in far enough, space itself becomes turbulent and uncertain. On the scale of the Planck length, about 10 to 35 meters, the very concept of distance might break down. Space might dissolve into a kind of quantum foam, with the smooth fabric of space-time becoming frothy and indeterminate. At that scale, according to some ideas, tiny bubbles of space-time could appear and vanish, and geometry itself might fluctuate wildly. Wheeler, a physicist, famously imagined the scene as the quantum foam, a churn of space-time at the smallest scales. Over sufficiently small distances and brief moments, the smooth geometry of space and time could erupt into a storm of random fluctuations. Imagine zooming into what looks like a smooth photograph, only to find it grainy with pixels at a certain magnification. These fluctuations could be large enough, on those scales, to cause significant departures from the smooth space-time we perceive at human scales, giving space a foamy, jittering character when examined ultramicroscopically. With our current technology and understanding, we cannot probe such minute scales directly. Our best theories, quantum mechanics and general relativity, don't play nicely together at this extreme, so we don't yet have a clear picture of what space truly looks like at the Planck scale. It's possible that space-time is not fundamentally smooth. It might be made of countless tiny units or threads. There is no definitive reason that space needs to be perfectly continuous. Perhaps, in a full theory of quantum gravity, space-time would consist of many small, ever-changing regions where space and time themselves blur and fluctuate. It's a mind-bending idea. The familiar continuity of space might, under magnification of 1033, break into a ceaseless fizz of tiny distortions and ephemeral particles popping in and out of existence. Yet black holes are not absolutely black. Quantum theory predicts that the vacuum near the event horizon of a black hole seethes with particle-antiparticle pairs. Occasionally, one particle from such a pair can be pulled into the black hole while the other escapes. To an outside observer, the black hole appears to emit a faint trickle of particles, a phenomenon known as Hawking radiation. Over inconceivably long periods, this process can cause a black hole to slowly evaporate, leaking its mass back out into space. This is another reminder that even the empty space near a black hole is full of activity. The vacuum isn't void at all. Its quantum fluctuations can have tangible effects, bleeding away the black hole's mass bit by bit. In this way, space acts as both giver and taker, swallowing light at the horizon, yet furtively returning energy to the universe through quantum processes. One place where we suspect this quantum nature of space becomes crucial is inside black holes, those mysterious abysses formed from collapsed stars. A black hole is a region where space is curved so extremely that once anything, matter or light, falls in, it cannot escape. The boundary around a black hole is called the event horizon. At that boundary, space is rushing inward at the speed of light, like a waterfall of space-time cascading into the hole. If you approach the horizon, time slows relative to the outside world, and the pull of gravity, the curvature of space, becomes overwhelming. To a distant observer, you would appear to slow and dim, never quite falling in, as your final light waves get stretched and weakened, a strange visual consequence of the way space and time warp. Beyond the horizon, all paths lead further inward, deeper into the hole. As you fall inside a black hole, you would experience space rushing you inexorably toward the center. According to general relativity, at the very center lies a singularity, a point of infinite density where space and time, as we know them, ends. In truth, this singularity is likely where our current understanding fails. Gravity is so extreme and the scale so tiny that quantum effects should dominate. Here, the smooth fabric of space might tear or blend with the quantum foam. The distinction between space and matter could blur. We don't yet have a theory of quantum gravity to tell us exactly what happens in such an intense intersection of the very large and the very small. Does space cease to exist as a meaningful concept at the core of a black hole? Are there atoms of space-time or quantum threads knitting things together beyond our view? We simply don't know. The laws of physics as we have them break down in these conditions. Physicists have proposed bold ideas to reconcile these deep conflicts. One radical suggestion is that space and time might not be fundamental at all, but rather emerge from something more basic and abstract. Some research hints that quantum entanglement, the ghostly interconnection between particles, may knit together the fabric of space itself. In certain theoretical models, the geometry of a region of space can be described entirely by the information, the entanglement connections, on its boundary. This is known as the holographic principle, suggesting that our three-dimensional space might in some way be a projection from information encoded on a distant two-dimensional surface. It's as if space could be woven from quantum threads of information. Another idea is that space-time is composed of tiny, discrete units, sometimes envisioned in approaches like loop quantum gravity, so that on the smallest scale, space is more like a woven lattice or network. These concepts are still speculative and hard to test, but they share a poetic point. They hint that space, for all its apparent continuity, might be an emergent illusion, like a tapestry that looks smooth from afar, but up close is made of fine threads. If so, there could exist degrees of freedom or building blocks of the universe more fundamental than space and time. What is space, truly? It may be that our familiar space is just the visible frosting on a much deeper reality. Facing these profound questions,
humanity has responded by inventing clever ways to probe the nature of space. We have built powerful telescopes that peer across billions of light years, effectively allowing us to look back in time and see the young universe when it was filled with hot plasma and newly formed galaxies. We have launched observatories above our atmosphere to measure the cosmic microwave background with exquisite precision, mapping its faint ripples to decode how space expanded and what it contains. We have devised experiments on Earth to test the nature of the vacuum. For instance, sensitive laboratory apparatus has confirmed the Casimir effect, detecting the slight pressure of vacuum fluctuations pushing two plates together. We smash particles together in giant accelerators, momentarily concentrating tremendous energy into tiny volumes of space, to glimpse how nature behaves at the highest energies and smallest scales. This endeavor led to the discovery of the elusive Higgs field that permeates space and endows particles with mass. We have even detected the subtle ringing of space-time itself using gravitational wave observatories like LIGO. These giant laser interferometers can sense when space stretches and squeezes by less than a trillionth of a centimeter as a gravitational wave passes. The first such detection in 2015 came from two merging black holes and was heard as a faint chirp, literally the sound, after conversion, of space briefly vibrating from a cosmic collision. Since then, we have caught multiple cosmic events via gravitational waves, black holes swallowing each other, neutron stars colliding and sending tremors through space. It's a completely new way of listening to the silent universe, using space itself as our messenger. We have also physically journeyed into space, albeit only a small distance so far in cosmic terms. Our robotic probes have ventured beyond the planets, sampling the environment of space directly. The Voyager 1 and 2 spacecraft, for example, have traveled beyond the influence of our sun's solar wind and entered interstellar space, the space between the stars. They confirmed that even the emptiest regions of our galaxy are not entirely empty. They contain traces of very thin plasma, ionized gas, and high-energy cosmic rays. Voyager 1, now over 23 billion kilometers away, is humanity's farthest messenger. It is sailing through the cold, silent void, reporting back that even out there, far from any star, there are a few atoms per cubic centimeter and faint whispers of magnetic fields and radiation. Its journey reminds us that space is not a distant void we go to. It's the ocean we've always been swimming in, now stretching out to greater and greater depths. We are not outsiders to the universe's expanse. We are an integral part of it. We move through space. We depend on it. We are composed of it. In a sense, we, conscious beings, are space's way of observing itself, the universe contemplating its own vastness through our eyes. From the space between galaxies to the space inside your chest, it is one continuous fabric. The next time you gaze up on a clear night and marvel at the darkness between the stars, remember that that darkness is not empty. It is the same space that cradles you, extending through and around you always. We tend to think of ourselves as down here and space as out there. But in truth, we have always been in space. From the moment of our birth, we have been enveloped by space. Space is not a distant domain only astronauts visit. It is the vast, subtle medium in which we live and breathe. When you look up at the night sky, you are looking into an extension of your own surroundings. The air ends not far above your head, and then space continues, unbroken, to the ends of the universe. So, what is space? It is not a mere nothingness, not a sterile void. It is the gentle scaffolding that holds all of creation. It is a medium that can bend and ripple, a vast field that carries light and nourishes the formation of stars. Space is the silence that allows the music of existence to be heard. It is the canvas on which the galaxies are painted. And yet the canvas itself has texture and influence beyond what our eyes see. Space is the invisible architecture of the universe, the foundation that connects all things.
It is often said that nature abhors a vacuum, but in truth, nature uses the vacuum, space, as the foundation for everything. Without space, there would be no room for light to travel, no separation for objects to exist apart, no time for events to unfold. Space is not the absence of things. It is the presence that allows things to be. It is the very possibility of anything and everything. As our journey through darkness and light comes to an end, we return to that initial quiet question and find a profound answer. Space is not an emptiness to be feared, but a presence to be revered. It is the quietly fertile nothing that makes everything possible. We float in it, we are made of it, and we are forever embraced by it. The invisible architecture of the universe surrounds and sustains us. Space is the darkness that cradles the stars, the silence that gives meaning to sound, the stillness that makes motion possible. It is the vast, living fabric in which the story of the cosmos and our own story is written. Space is the womb of the universe, the canvas of creation. It is not an absence, but the gentle yet all-encompassing presence that allows all things to be. Night on Earth. The air is still and the sky is moonless and dark, spangled with stars. A soft band of milky light arches overhead, the Milky Way, our galaxy seen from within. Standing here, we gaze up and out at the universe. Each pinpoint of starlight that reaches our eyes is ancient. Each carries a story across time. Light is the great messenger of the cosmos. A photon departs the surface of a distant star and journeys for years, centuries, millennia through the interstellar abyss, finally ending its voyage in the pupil of an eye or the lens of a telescope. When we catch that faint glow, we are witnessing a memory. We see the star not as it is now, but as it was long ago when that photon began its journey. The night sky is a tapestry woven of past moments. Every glimmer is a relic of history, a tiny time capsule ferrying the past into the present. Each of those ancient photons is like a message in a bottle, cast into the cosmic ocean eons ago, and only now reaching our shores. Consider the stars scattered above. The nearest, aside from our sun, shines with light that left it a few years ago. Others are so distant their light set out while ancient civilizations on Earth were rising and falling, or even before humanity existed at all. And yet, here and now, their ancient light touches us. In this way, observing the galaxy is an act of bridging time. We collect the aged light of countless suns and piece together what it tells us. Observation is a kind of gentle time travel, not moving ourselves, but receiving echoes from distant years and distant places. On the clearest nights far from city lights, the Milky Way's band is breathtaking. It spills across the sky like a luminous river. To the unaided eye, it is a faint, cloud-like glow, but through that glow, we sense depth, as if we are peering into a crowded metropolis of stars, far away. Long ago, we could only wonder what this milky band actually was. Was it a path of souls, a backbone of night, a river of milk from a goddess? Indeed, the very name Milky Way comes from an ancient Greek myth that it was formed by milk sprayed from the breast of the goddess Hera. It took the curiosity and ingenuity of observers over centuries to unravel the truth. That band is the combined light of billions of stars, too distant and faint for us to resolve individually. We came to realize we are inside a vast disk of stars, a galaxy, and that the Milky Way's shimmer is our edge-on view of that disk. Imagine Galileo in 1610, one of the first people to turn a telescope to that soft blur of the Milky Way. In his small scope, the haze resolved into countless tiny points. The Milky Way was not a celestial cloud or fluid. It was composed of uncountable stars. This was a revelation, our first glimpse into the true nature of our galaxy. Later, astronomers mapping the sky noticed that those stars thickened in one particular direction, hinting that the center of this starry system lay somewhere behind the constellations of Sagittarius and Scorpius. Slowly, a picture formed in human understanding. We live within a flattened congregation of stars, like a great starry whirlpool. Our sun is but one star among many in this cosmic ocean. Now, as we stand under the stars, we appreciate something profound. We are inside the very structure we are trying to understand. Any map we make of the galaxy must be assembled from our viewpoint embedded within it. It's as if we are trying to discern the shape of a vast forest while being deep among the trees, or like attempting to read an enormous book while standing on one of its pages. We cannot step outside the Milky Way to see it whole. We must infer its form through careful observation and imagination. And so, we observe. We watch the heavens with every tool we can craft, collecting light in all its forms. We gather photons like alchemists, gathering whispers of truth. Each telescope, each detector, is an extension of our eyes, allowing us to see a bit farther, a bit clearer, or in types of light invisible to our eyes. With patience and ingenuity, we learn to decode the messages that light carries, the subtle shifts, colors, and timings that reveal distances, motions, and compositions. From tiny clues, we begin to perceive the grand structure that we inhabit. Think of the sky above as a grand mosaic. Each star's light is one tile in that mosaic. By studying those tiles closely, their color, their brightness, their position and movement, we start to discern the larger image they form. We realize that the faint band of the Milky Way is not uniform after all. It has structure. Brighter patches within it appear as soft, luminous swells, which we now know to be star clouds, densely packed regions of stars in our spiral arms. Dark gaps and notches, such as the Great Rift splitting the Milky Way in the summer sky, are not empty of stars at all, but shrouded by intervening dust clouds that block their light, creating black silhouettes against the glowing backdrop. Even our naked eye view hints at the galaxy's form. We see a bulging brightness toward one end of the band, toward the constellation Sagittarius, the direction of the galactic center, and a tapering, thinner glow extending around the sky toward the opposite end, the galactic anticenter in Auriga. The peoples of the southern hemisphere, for example, saw dark constellations in those dusty rifts, an emu in the sky, a great coal sack. Our ancestors spun tales of this band of light. Today, we understand it as the plane of our galaxy's disk, full of stars and shadowed by dust. As we drink in this sight, we find it humbling and wondrous. We are looking at our galaxy from the inside, using shards of ancient light to guide us. In that gentle glow lies everything: the collected radiance of distant suns, the imprint of interstellar clouds, the secrets of our galaxy's architecture waiting to be teased out. The journey to comprehend it is only beginning as we stand here, eyes upward and hearts open to the stellar chorus of light and time. But looking is only the first step. To truly understand this galaxy we call home, we need to measure and map it. How can we gauge the distance to those countless stars? How do we chart a landscape so vast while confined to a single speck within it? Over time, we learned to coax more information from the starlight, turning observation into a precise language. One of our earliest triumphs was discovering the method of parallax, the same effect you notice if you hold out your hand and close one eye, then the other, watching your finger seem to jump against far background objects. Our Earth, in its orbit around the Sun, provides a baseline 300 million kilometers wide. Every 6 months, as we stand on opposite sides of the Sun, nearby stars appear to shift slightly against the far background. It's a tiny, subtle wobble, imperceptible to the unaided eye, but with careful instruments we can measure it. By this minuscule celestial geometry, we determine how far away those stars are. The closer a star, the more it appears to shift. For the first time, the vast void between stars had a measurable scale. We learned that even the nearest stars are tens of trillions of kilometers away, billions of times farther than any voyage our species has ever taken. and more distant ones, hundreds or thousands of times farther still. The galaxy opened up in 3 dimensions, depth unfolding from what once was a flat panorama of lights. Imagine watching a particular nearby star through the year. In January, it's aligned just so with some distant background galaxy. By July, it has traced a tiny loop in the sky. That loop is the imprint of Earth's journey around the Sun, reflected in the heavens. From that trace, we triangulate the star's distance, like a surveyor mapping unseen lands from 2 vantage points. These measurements, painstaking at first, have now become an exquisite survey on a grand scale. Today, satellites with sharp electronic eyes measure parallaxes for over 1 billion stars, pinpointing their positions in space. With this technique, our stellar maps gained reliable depth. We began to know where we are and where other stars are in relation to us. Not just their direction, but their true distance in light years. Distance alone, however, is only part of the story that light can tell. The stars have motions of their own. They are not fixed jewels set in the firmament, but travelers orbiting the galactic center, each on its long journey around. Seen from our moving Earth, their motions across the sky are subtle and slow. But if we observe carefully over years and decades, we discern a drift. A star in the Big Dipper creeps forward. A bright neighbor slides subtly southward. Tiny changes in the constellations that over centuries will alter the sky's familiar patterns. This is proper motion, the apparent motion of stars across the sky as they sail through space. Early astronomers discovered a few nearby stars with noticeable proper motion, like Barnard's star, which moves faster across the sky than any other, about the width of the full moon every 200 years. Now, with modern detectors and long-term observations, we find that nearly every star has some motion. They are all participants in a grand dance, circling the center of the Milky Way at various speeds and angles. By measuring these motions for millions of stars, we begin to trace the currents and streams of our stellar city. We see which stars move together like schools of fish, perhaps born together in long dispersed clusters. We see which stars speed along faster or slower than average, which ones are plunging toward the center or flying out toward the fringe. The patterns of movement hint at the gravitational forces shaping them, drawing the unseen outline of the galaxy's mass and structure. As we map these stellar motions, we find, for example, that our Sun and its neighbors are all streaming in roughly the same direction around the galactic core, like autumn leaves caught in a slow eddy of wind. But some stars, often those outside the main disk or high above it, move quite differently, perhaps on steeply inclined or retrograde orbits that carry them far above and below the disk plane. These are clues to the galaxy's structure and history encoded in motion. We gather them eagerly, knowing each is a piece of the puzzle. Starlight carries yet more information hidden in its delicate spectrum, the rainbow spread of its colors. When we pass a star's light through a prism or a spectrograph, we see not just a continuous band of color, but a barcode of dark lines and bright lines. These are the fingerprints of elements within the star's atmosphere. Each chemical element leaves its mark by absorbing or emitting specific wavelengths of light. By reading this stellar code, we learn the star's composition, how rich it is in heavier elements forged by previous generations of stars. We learn its temperature and hints of its age. For instance, a star rich in metals, elements heavier than helium, is likely younger, formed after earlier stars seeded the galaxy with those metals. We also find, within those spectral lines, that many are shifted slightly from where they'd be if the star were at rest. Some lines are nudged toward the blue end of the spectrum, others toward the red. This is the Doppler effect, the same phenomenon that makes a siren's pitch rise as it rushes toward you and fall as it recedes. For starlight, a blue shift means the star is moving toward us. A red shift means it is moving away. Thus, the spectrum gives us the star's velocity along our line of sight.
its radial velocity.
Now picture this. We have parallax, giving us distance, proper motion, giving us sideways movement across the sky, and spectral shifts giving us motion toward or away from us. Combine these, and for the first time, we can know a star's true motion in three-dimensional space. We can watch the galaxy's internal traffic, not just as a flat image, but as a dynamic, moving reality. With powerful surveys and observatories, astronomers have measured the velocities of millions of stars, compiling a vast catalogue of stellar motions. It is as if we have surveyed a great flock of birds in flight and traced each bird's path through the sky. From within, we map the Milky Way, not as a static snapshot, but as a living system, stars orbiting in the common gravitational field we all share. Each piece of data, a distance, a proper motion, a spectral signature, is a thread. Woven together, those threads create a rich tapestry, a model of our galaxy as it is, and, in a way, as it was, since even the motions of stars carry information about past events and the galaxy's evolution. We see, for instance, groups of stars moving in unison, perhaps born together in the same long-ago star cluster that has since dispersed, their common motion betraying their kinship across space. We find stars speeding unusually fast or slow for their location, hinting at gravitational perturbations or past encounters that have stirred the pot of the galaxy. Yet, even with such data in hand, mapping our galaxy from within remains an exercise in inference and imagination. There are still vast areas veiled to us, distances too great for parallax to reach directly, motions too subtle to detect within a human lifetime. We calibrate and extend our reach by using standard candles, special objects of known luminosity, such as certain variable stars or stellar explosions, which allow us to gauge distance by how faint they appear. We extend our velocity map by measuring not just individual stars, but also the bulk motion of star clusters and gas clouds. We are like explorers mapping a continent by combining local surveys, careful to stitch them into a coherent whole. It's a formidable challenge, but bit by bit, the dimensions of our Milky Way are coming into focus. Consider what we have learned through these patient endeavors. We know the Sun lies about 26,000 light-years from the galactic center, roughly halfway out along the Milky Way's radius. We know our galaxy is a rotating disk because we can sense the systematic motion of stars around the center. For example, stars on the inner side of the Sun, towards Sagittarius, are, on average, coming toward us, blue-shifted, as they overtake us on the inside track, while those on the outer side, toward Auriga, are receding, red-shifted, as we move away from them, indicating the entire disk spins. We know the scale of this rotation. The Sun and its neighbors are hurtling along at roughly 220 kilometers per second on this colossal circuit. Even at that immense speed, one full orbit around the galaxy, a galactic year, takes on the order of 200 million years. Our Sun has made only about 20 such orbits in its 4.5 billion year lifetime. When last it was in this same position in its orbit, the first dinosaurs were emerging on Earth, and the continents had a different arrangement. On its next pass, 200 million years from now, who knows what life, or what changes on Earth, will see the galaxy from our Sun's vantage. To put this in perspective, if the Milky Way's rotation were sped up so that one galactic year lasted a single human day, then all of recorded human history would flash by in just a fraction of a second. Our lives are impossibly brief compared to the immense cycles of the galaxy. As we enrich our map with measurements, we also engage in an act of imagination. We convert data points into a mental journey. Let us embark on that journey now, to envision the Milky Way from our local neighborhood outward, using all we have learned. Through careful observation, we have gathered enough clues to sketch the grand design of our home galaxy. It is time to leave our little perch near the Sun and travel, in our minds, across the vast expanse of the Milky Way. guided by the light and motions we have collected, like navigators following a cosmic compass. Our journey begins in the quiet suburb of the galaxy where the sun resides. Here, roughly halfway between center and edge, the stars are relatively sparse. We are in a minor spur or branch of a spiral arm, not one of the Milky Way's big arms, but a smaller local lane of stars and nebulae. This feature is sometimes called the Orion Spur, our local side street off a major arm. Drifting outward from the sun, we soon encounter one of the great spiral arms proper, the vast curving streams of stars and gas that wind around the galaxy. It looms ahead like a bright cloud on the cosmic horizon, a tremendous glowing avenue in space, studded with clusters of brilliant blue stars and embroidered with luminous nebula. In these nebulae, immense clouds of gas and dust, new stars are being born. We pass by a stellar nursery where hot, newborn stars light up the surrounding gas in pink and lavender hues. Nearby, a tight cluster of young stars shines brightly, their ultraviolet light causing the remaining gas of their parent cloud to fluoresce. This is the vibrant realm of the spiral arms, where star formation continually renews the galaxy. These spiral arms are the most striking features of the galactic disk. They wind outward from the center in a graceful spiral pattern, like the swirls of a giant pinwheel. Each arm is not a solid structure, but a kind of density wave, a traveling traffic jam of stars and gas. As this wave moves through the galactic disk, it compresses gas clouds and triggers star formation, leaving a wake of bright young stars that outline the arm's shape. We see these arms as glittering, starry ribbons. Along them live massive, short-lived stars that burn hot and blue and die young, so they never stray far from their birthplaces, thus tracing the spiral pattern in glowing neon blues. Meanwhile, older stars, like yellow suns and ruddy red dwarfs, are found everywhere, even between the arms, but they are dimmer and do not stand out as boldly to our eyes. Our own sun, a middle-aged yellow star, drifts in a quieter region between two major spiral arms, essentially in the galactic suburbs, far from any bustling stellar metropolis. We are situated between the nearby Sagittarius Carina arm, closer to the center, and the Perseus arm, toward the outer galaxy, in a calmer spur that branches between them. Generations of stars have come and gone here, long after the grand spiral pattern was established. As we continue our journey through the disk, we notice that it is indeed a disk, a relatively thin plane compared to its vast width. The Milky Way's disk is often likened to a cosmic frisbee or pancake, about 100,000 light-years across but only a few thousand light-years thick. In fact, the part of the disk where star formation actively occurs, the thin disk, might be only 300–500 light-years in thickness in the solar neighborhood, thicker toward the center. This thin disk is where most of the interstellar gas resides, where spiral arms shape the cosmic traffic, and where bright young star clusters light up the scene. It is flat because, as our galaxy rotates and evolved, collisions and angular momentum caused most matter to settle into this plane. Let's rise gently a bit above this cosmic plane to gain perspective. From just above the disk, looking down at a slight angle, the Milky Way's layout becomes apparent. We see that the Milky Way isn't just a single flat disk of stars, but has layers and structures. Above and below the bright thin disk, there is a sparser, thicker distribution of stars, appropriately called the thick disk. The thick disk consists of older stars with fewer heavy elements, spread over a greater range of heights above and below the plane. These stars move on orbits that are inclined relative to the plane and have a wider variety of paths than the stars of the thin disk. The thick disk doesn't contain the bright gas clouds or young clusters that define the spiral arms. It is more like a fossil record of an earlier epoch of our galaxy, or perhaps the result of an ancient merger that puffed up the stellar distribution. Its presence gives the Milky Way a faint extended glow when viewed edge-on, a kind of dim, broad corona of stars through which the brighter thin disk is threaded. Returning to the plane, we journey further inward toward the galactic center. As we travel deeper toward the core, the stars around us multiply and crowd together. The sky grows richer with starlight. By the time we are halfway to the center, the star density is noticeably higher than in our neighborhood. We pass through another spiral arm, the Sagittarius arm, packed with stellar nurseries and clusters. Here, we see the remains of titanic stars that have lived and died. For example, a great supernova remnant, an expanding shell of gas from an exploded star, its filamentary tendrils glowing with the energy of the blast. Such remnants dot the interstellar space here, markers of past star deaths. The interstellar medium grows denser and more turbulent. Radio telescopes mapping this region reveal complex networks of cold hydrogen gas and molecular clouds, gathering like thunderstorms in the distance, awaiting the next trigger to form new stars. Moving nearer to the core, the spiral arms begin to converge and blend into a continuous, luminous mass. The distinction between individual arms blurs in a flood of starlight. We are entering the central bulge of the galaxy. This bulge is a huge, rugby ball-shaped or peanut-shaped concentration of stars at the galaxy's center. Here, the average age of stars increases. Many are old, swollen red giants that have shone for billions of years. The light takes on a warmer, reddish tint, dominated by these cooler old stars, and the interstellar gas is scarce. Most of it was long ago converted into stars or cleared out by supernova. In the bulge, stars are so numerous that the night sky from a planet deep in the bulge would be ablaze with thousands of stars visible to the naked eye, far brighter and more numerous than the sky we know. It would never get truly dark. When we observe the Milky Way's central bulge from Earth's skies, we are looking at this crowded hub from 26,000 light-years away, seeing it through dust that dims and reddens its light. The very heart of the Milky Way is a crowded, dynamic place. In addition to the swarming stars, there are mysterious radio sources, X-ray flashes, and high-energy phenomena. At the exact center lies something both invisible and immensely powerful, a supermassive black hole around which the entire galaxy revolves. We call this central dark object a black hole, but we might also think of it as the gravitational heart of the Milky Way. We have detected it indirectly by watching stars orbiting at fantastic speeds around an apparently empty spot in the bulge. Indeed, over decades, astronomers watched individual stars near the galactic center loop around this invisible point. One star completed a full oval-shaped orbit in just 16 years, reaching a mind-boggling velocity of over 5,000 kilometers per second at its closest swing by the unseen mass. These observations allowed us to pin down the mass of the hidden object, about 4 million suns, confirming that nothing but a black hole could concentrate so much mass in so tiny a space. Occasionally, this dark giant announces itself. If a stray cloud of gas wanders too close, the black hole's gravity rips it apart, and the infalling gas heats up and emits powerful X-rays before vanishing. For the most part, however, our galaxy's central black hole is quiet, a sleeping titan. In 2022, this inference was dramatically confirmed when astronomers captured a direct image of the region just outside the black hole's event horizon using a global network of radio telescopes. The result was a telltale ring of light, radiation from superheated gas orbiting the black hole, surrounding a dark shadow. For the first time, we saw the shadow of our galaxy's black hole, a sight that would have been unimaginable not long ago. What would it be like right next to that heart of darkness? If we could safely drift in the innermost region, we might see the fabric of space itself being warped by the black hole's gravity. We wouldn't see the black hole itself, it would be a void, but we might observe stars whipping around it in tight orbits and flashes as doomed material falls in. Around the black hole, within a few light years, is a nuclear star cluster. a densely packed cluster of stars orbiting furiously. Some of these stars are young and massive, paradoxically forming in the fierce environment near the black hole. How they came to be there is still debated. Perhaps their birth was triggered by the compression of gas streaming into the center. This cluster, along with the black hole, forms the dynamical hub of the Milky Way. If we could somehow hover above the galactic center and look down from far overhead, we would also notice that the Milky Way has a long, bar-shaped concentration of stars stretching across its central region. Our galaxy, as it turns out, is a barred spiral. The central bulge is slightly elongated into a bar that extends on either side of the center for a few thousand light years. The bar rotates slowly, and it acts like a gravitational funnel, channeling gas from the outer galaxy inward along its sides. The spiral arms of the Milky Way actually emanate from the ends of this bar, rather than directly from a circular bulge. The existence of the bar was discovered through infrared observations, since the bar's stars are often hidden behind dust in visible light. In the tumult of the inner galaxy, the bar is another piece of the puzzle, a structural backbone supporting the inner spiral pattern. Gas flows inward along the bar and collects near the center, where it can fuel bursts of star formation or feed the black hole. Having experienced the brilliance of the galactic core, with its tightly packed stars and mysterious dark center, let us now journey outward again, this time away from the bright plane of the galaxy. We climb above the disk, moving perpendicular to the plane of the spiral, as if riding a beam of light straight up from the central region. As we rise, the full layout of the Milky Way's structure reveals itself in our mind's eye. Below us spreads the flat disk with its winding spiral arms, a whirl of starlight patterned by dark lanes of dust. We see the central bulge as a luminous peanut-shaped glow in the middle, with the straight bar cutting through it. The spiral arms trail off from the ends of the bar, curving gracefully around the galaxy's center. From this vantage point, the grandeur of the Milky Way is unmistakable. A barred spiral galaxy, one among billions in the universe, yet special to us because it is home. The combined starlight in the disk forms a hazy, glowing lens, crossed by the intricate silhouette of dust clouds. Those dust clouds, which from within appear as dark rifts, from above trace the spiral structure, particularly prominent along the inner arms and the bar, where concentrations of gas and dust are highest. Continuing farther up and out, the bright disk begins to shrink below us, contracting to a concentrated band of light. Now the surrounding environment grows darker and more diffuse. We have entered the stellar halo of the galaxy. The halo is a roughly spherical region enveloping the Milky Way, extending far beyond the disk in every direction. It contains only a tiny fraction of the galaxy's stars, so out here space is almost empty. The stars we do encounter in the halo are often very old, solitary wanderers, perhaps one here, another dozens of light years away, in stark contrast to the bustling crowds in the disk. Yet occasionally, we come across a grand sight, a globular cluster. Imagine floating into one of these clusters. Suddenly, the star density increases immensely, and you find yourself in a ball of hundreds of thousands of stars all around you, bound together by gravity. Astronomers have discovered around 150 of these globular clusters orbiting our galaxy. In a globular cluster's core, the night sky of a planet would be carpeted with countless brilliant suns, many more and closer than the stars we see from Earth's skies. These clusters are cosmic time capsules. Their stars are extremely old and metal-poor, lacking in heavy elements. They likely formed when the galaxy itself was young, before the disk fully developed, or even in small proto-galaxies that later merged to become the Milky Way. Now these clusters orbit in the halo, following long tilted elliptical paths that carry them far above and below the galactic plane. Scattered among the halo's sparse stars and globular clusters are also traces of past galactic meals,
faint streams of stars rippling through space, the remnants of dwarf galaxies shredded by the Milky Way's gravity. We might not notice them with the naked eye, but our measurements reveal coherent trails, hundreds of stars moving together along the same orbit, stretched out across tens of thousands of light years. These are the ghostly footprints of galaxies the Milky Way devoured long ago, their stars now part of our halo, still traveling in the path of their original small galaxy. One of the most prominent of these streams comes from the Sagittarius dwarf galaxy, a satellite galaxy currently being torn apart. Its stars have been pulled into a long ribbon that wraps around our galaxy like a gossamer scarf. Only recently, thanks to exquisitely precise maps of star positions and motions provided by a space observatory scanning over 1 billion stars, did this substructure become crystal clear in our data, a fossil record of a cosmic merger, finally exposed by careful archaeology of the halo. The halo, then, is not a tranquil, empty realm after all, but a graveyard of sorts, and also a nursery of history, containing the debris of ancient mergers and the oldest survivors from the Milky Way's youth. Despite how far we have come, the influence of the Milky Way extends farther still. Encompassing all of this, the disk with its stars and arms, the bulge and bar, the stellar halo with its clusters and streams, is the galactic halo of dark matter. We do not see it, but we feel it in the motions of everything bound in the galaxy. The dark matter halo is enormous and massive. If we could somehow see it, it might appear as a vast, dim sphere enveloping the visible galaxy and extending hundreds of thousands of light years out. The visible Milky Way, the stars, nebulae and clusters we can photograph, is like the bright kernel at the center of an immense, unseen cocoon of dark matter. This invisible halo holds the galaxy together with its gravity. It is as if an unseen hand holds the entire galaxy in its grasp. Without it, the outer stars and gas would not be moving as fast as they do. They would drift away, unable to remain bound to the galaxy. In fact, astronomers deduce that around 85 to 90% of the Milky Way's mass must be in this invisible form of matter, leaving only 10–15% in all the stars, gas, and dust we can see. The luminous portions of the Milky Way are truly just the tip of a cosmic iceberg. The dark matter provides the additional gravity needed to keep the galactic disk intact and the outer stars tied to the whole. In our journey, though we cannot detect this dark component directly, we are always moving within it. It surrounds and permeates our galaxy, a silent partner in its evolution. Now, in our imagination, we have traced the structure of the Milky Way from our local neighborhood out to the farthest reaches, a shining spiral disk of stars with majestic curving arms, a central bulge, crossed by a bar, housing a supermassive black hole at its core, a surrounding halo of ancient stars and globular clusters, and mysterious dark matter, and an extended spherical cloud of dark matter encompassing it all. This is the architecture of our island universe, as we understand it today, gleaned from measurements painstakingly collected from our station inside the disk. It is an awe-inspiring vision, especially knowing that just a century ago, humans did not even know for certain that our galaxy was one of many. Only in the 1920s did we confirm that the Milky Way is indeed a galaxy of a particular size and shape, and that countless other galaxies pepper the cosmos beyond our own. The Milky Way itself is now estimated to span about 100,000 light-years from end to end, containing a few 100 billion stars. Our galaxy is immense, yet it is also just one member of a much larger cosmic community. For countless generations, our view of the Milky Way was limited to that hazy band of light in the sky and the visible stars around us. It is only in the last century that we have developed the means to extend our sight beyond the visible. Radio telescopes tuning in to invisible wavelengths, infrared detectors that can peer through dust, space telescopes above the blurring atmosphere, and more. Each new technology opened a fresh window onto our galaxy. With these tools, astronomers discovered a very different Milky Way, hidden behind the one our eyes perceive. A galaxy of radio glows and infrared heat, of X-ray flashes and gamma-ray bubbles. Consider the problem of dust. Invisible light, those dark rifts and patches that stripe the Milky Way, notably the Great Rift through Cygnus and Aquila and the famous coal sack in Crux, are caused by clouds of interstellar dust blocking the light of stars behind them. These dust clouds, though accounting for only a small fraction of the Milky Way's mass, loom large to our eyes because they obscure the stellar backdrop. Along the galactic plane, dust prevents us from seeing into the far distance in visible light. It creates a zone of avoidance where optical astronomy cannot penetrate. But dust's invisibility cloak has a weakness. It is far more transparent to longer wavelength light like infrared and radio. Imagine we could switch our vision to the infrared. The night sky would transform. Those dark dust lanes that cut the Milky Way's band would begin to glow softly because the dust itself emits infrared light, having been warmed by starlight. The veil of dust thins dramatically. Stars previously hidden behind dust clouds come into view. In infrared, one can peer straight through many of the dust clouds that block optical light. The galactic center, which to human eyes is hidden behind opaque dust in Sagittarius, now blazes forth in infrared images as a crowded, brilliant hub of stars. Early infrared sky surveys, pioneered in the 1960s and 70s, and dramatically improved with space telescopes in the 1990s and 2000s, revealed the central bulge and the long bar of the Milky Way clearly for the first time, confirming what radio and star count data had hinted. We see that the bulge is full of old, cool stars, dim in visible light but bright in infrared, and that the spiral arms are dotted with warm dust clouds in star-forming regions. The entire disk emerges in infrared as a continuous ring of light encircling the sky, no longer interrupted by dark gaps, a continuous Milky Way unbroken by dust. Now, let's shift to even longer wavelengths and open our radio eyes. In radio waves, the individual stars largely vanish from view. Stars emit relatively little radio energy, but other features emerge loud and clear. One of the most important radio emissions in the galaxy comes from neutral hydrogen gas. Every hydrogen atom in interstellar space can emit a faint radio signal at a wavelength of 21 centimeters. By tuning into that frequency, astronomers in the mid-20th century effectively heard the whispers of the Milky Way's vast clouds of hydrogen. They mapped the distribution of this gas throughout the sky. What they found revolutionized our understanding. The Milky Way's disk is traced by immense spiral-patterned streams of hydrogen gas, extending far beyond where most of the stars are. By tracking the Doppler shifts of this 21-centimeter emission, astronomers could chart the rotation of the galaxy and identify its spiral arms, even on the far side of the galactic center, which no optical telescope could ever see. Through radio eyes, the Milky Way's spiral structure was drawn out in detail, including portions of arms hidden behind the bulge. The zone of avoidance that plagued optical astronomy was no obstacle to radio waves. They passed through the dust and revealed that beyond the center, the galaxy continues in symmetrical splendor. In the radio view, we also see things our eyes never could. The flicker of pulsars, rapidly spinning neutron stars, sending lighthouse-like beams of radio waves. The glow of supernova remnants, where shock waves accelerate electrons to emit radio waves as they spiral in magnetic fields, and a diffuse background hiss of radio noise permeating the galaxy, caused by a combination of free electrons moving through magnetic fields and the distant multitude of unresolved sources. The center of our galaxy, in radio wavelengths, is actually one of the brightest sources in the sky. A strong radio source, called Sagittarius A, marks the location of the central black hole and its immediate surroundings. This was how the black hole was initially inferred, before the stellar orbits and images confirmed it.
In radio waves, the Milky Way appears not as a single band of light, but as a complex structure. A band of emission from the disk, visible even in daytime with the right instruments, punctuated by bright spots, supernova remnants, pulsars, star-forming complexes, and with a bright, compact source at the center, the black hole's environment. Now imagine tuning our vision to shorter wavelengths than visible, into the ultraviolet. The scene shifts once more. The ultraviolet view highlights the youngest, hottest stars and the regions of active star formation. Many of the ordinary stars and red giants that dominated the infrared now fade into darkness in UV, as they are too cool to emit much at these energies. In their place, glittering like blue-white sparks, are the massive O and B-type stars, blazing fiercely with ultraviolet light. We would also see glowing nebulae, like the Orion Nebula, under the assault of intense UV radiation from these hot stars, appearing even brighter relative to the background. The spiral arms in UV are delineated strongly by these short-lived stars and their associated HII regions, ionized gas clouds. The galactic center's old stellar population would fade in UV, making the bulge much less prominent, but any regions of recent star formation or accretion near the center would stand out. The UV view, then, is a portrait of the Milky Way's vitality, emphasizing the sites of current starbirth and the presence of the hottest young stars. If we push to even more energetic extremes, into the realm of X-rays, the Milky Way we perceive changes almost entirely. Gone is the continuous sweep of billions of normal stars. Those stars are too cool and quiescent to shine in X-rays. Instead, the X-ray sky is dominated by rarer, high-energy objects, the end states of stellar evolution and violent cosmic events. We see the ghostly shells of supernova remnants filled with million-degree gas, glowing in soft X-rays. We see binary star systems where a neutron star or black hole is accreting matter from a companion. Such systems appear as point-like X-ray sources scattered through the disk, each a tiny beacon signaling where extreme gravity is at play. The dense star cluster at the galactic center lights up in X-rays due to hot gas and perhaps many small neutron stars and white dwarfs interacting. The supermassive black hole itself, usually quiet, occasionally flares, and those flares would make it a flickering X-ray source. We also detect a diffuse X-ray glow across the sky, especially toward the center and halo, indicating extremely hot, thin gas pervading the space around the Milky Way, likely a corona of gas heated by myriad supernova explosions, forming a kind of galactic atmosphere extending far into the halo. One of the most breathtaking discoveries of the past decade comes when we peer in the gamma-ray spectrum, the most energetic form of light. In gamma rays, much of the normal galaxy disappears. What remain are the signatures of cosmic ray interactions and exotic phenomena, and looming over the center, unexpected and huge, are the Fermi bubbles, two enormous lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane. Discovered by the Fermi Gamma-Ray Space Telescope in 2010, these bubbles are invisible in lower-energy light, but in gamma rays they glow as gigantic balloon-like structures. Their shape and extent suggest a powerful burst from the galactic center in the relatively recent past, perhaps a few million years ago, maybe a period of intense star formation, a starburst, or an active phase of the central black hole that drove energetic outflows. The Fermi bubbles reveal that the influence of the galactic center isn't confined to the disk. It has extended far into the halo. They are like a pair of cosmic chimneys, funneling energy from the nucleus out into space. Only by looking in gamma rays did these features become apparent, reminding us that each new way of seeing can unveil an entirely new facet of reality. Each of these different eyes on the galaxy, radio, infrared, visible, ultraviolet, X-ray, and gamma ray, tells a different part of the story.
Yet they all describe the same Milky Way. Layer by layer, by combining these multi-wavelength views, we assemble a richer, more complete portrait. The dark, obscuring dust that frustrated optical astronomers becomes, in the infrared, a gentle glow and a transparent window to the distant reaches. The cold hydrogen gas that is invisible to our eyes comes alive in the radio, mapping out the spiral arms even on the far side of the galaxy. The ultraviolet shows us the high-energy heartbeats of the galaxy's ongoing starbirth, while the X-ray and gamma-ray views reveal the violent endpoints and energetic feedback that shape the Milky Way, from exploding stars to feeding black holes. We also begin to utilize cosmic messengers beyond light itself. Detectors on Earth have caught fleeting blasts of neutrinos, ghostly subatomic particles, from a supernova in a nearby galaxy, and observatories are now listening for gravitational waves, ripples in space-time, that could emanate from neutron star mergers or other extreme events in our own galaxy. These new forms of seeing, neutrino and gravitational wave astronomy are still in their infancy, but they hold the promise of yet further insight into the hidden workings of the Milky Way in the future. Picture the experience of gradually shifting through these wavelengths as a kind of cosmic symphony for the senses. The Milky Way is playing multiple melodies at once. The visible light is the familiar tune, the majestic sweeping string section full of rich harmonies, the billions of stars. The infrared adds depth, the lower woodwinds, an undercurrent revealing the warm glow of dust, and the smoother distribution of old stars behind the veil. The radio brings in the percussion, rhythmic beats from pulsars, the steady hum of hydrogen clouds, the crash of supernova remnants, outlining structure with a deep, resonant background. The ultraviolet is like a bright trumpet fanfare, highlighting the most energetic star-forming regions with its bold, high notes. The X-ray might be an electric guitar riff or a sharp violin stab, sudden, intense accents from rare violent events. And the gamma ray is an almost unheard, ultra-high note, a subtle yet profound presence marking the galaxy's most extreme outbursts. When the entire orchestra plays together, we hear the full symphony of the Milky Way, each instrument contributing its part to a masterpiece far richer than any single wavelength alone could convey. Through multi-wavelength astronomy, the limits of our sight have been greatly extended. What once was a narrow, partial view, the Milky Way as a pale band to human eyes, is now a complex, multi-layered vision. The so-called zone of avoidance in the sky has largely been conquered. Infrared surveys reveal stars hidden behind dust. Radio surveys discover even distant galaxies lying beyond the Milky Way that were once obscured. Within our galaxy, no corner remains completely unknowable just because of dust. We have the tools to probe even the most hidden nurseries of stars. We can now map the structure of the Milky Way in its entirety, even where thick nebulae lie in the way. We can see the galactic center in its full glory behind the dust, witness starbirth sites otherwise invisible, and detect the faint echoes of past eruptions that no eye could ever see. Still, each improvement in vision often reveals new mysteries. For instance, the discovery of the Fermi bubbles in gamma rays answered the question of whether our galactic center had experienced a powerful recent outburst, but it also raised new questions. What exactly caused these bubbles? A burst of star formation blowing a galactic wind, or a period when the central black hole devoured a large amount of matter and expelled jets? Why do they appear so sharp-edged and symmetric? We also found hints of smaller, microwave-emitting bubbles closer in, and X-ray chimneys extending from the center, possibly all part of the same story. Every puzzle we solve yields new puzzles to ponder, and there remain portions of the spectrum and other messengers, neutrinos, gravitational waves, where the Milky Way has more to tell us. Yet, taken together, the information we've gathered gives us a truly spectacular understanding of our galaxy. We have learned not only what the Milky Way looks like, but how it came to be and how it is evolving. This brings us to consider the Milky Way not just as a static structure, but as a dynamic, living system with its own history, a history written in the stars. The Milky Way, magnificent and dynamic as it is today, is also very old. Its present form is the result of billions of years of evolution, a story written in the motions and compositions of its stars. Just as a geologist reads layers of rock to uncover Earth's history, or an archaeologist studies artifacts to piece together ancient civilizations, astronomers have learned to read the fossil record of our galaxy. The clues are subtle. The motions of stars, their chemical compositions, their ages, their distributions in space. By deciphering these clues, we are uncovering the Milky Way's biography, how it was built, piece by piece, from the deep past to the present. One of the most telling clues is the chemical makeup of stars. When the universe began, in the Big Bang, it consisted almost entirely of hydrogen and helium, with virtually no heavier elements, what astronomers call metals. Heavier elements like carbon, oxygen, iron, and gold were forged later in the hearts of stars and in supernova explosions. Each generation of stars enriches the cosmic material a little more with these elements. Thus, a star's metallicity, the fraction of its material that is heavy elements, serves as a kind of timestamp. An old star, born when few generations had lived and died before it, will be extremely metal-poor, nearly pure hydrogen and helium. A younger star, born after billions of years of cosmic alchemy, will inherit a higher proportion of metals. Now, when we survey stars in our galaxy, we find a striking pattern. The stars in the halo and those in globular clusters are generally very metal-poor. They contain only tiny traces of elements like iron or calcium, maybe 1,000th of what the Sun has. These stars are fossils of the early Milky Way. They formed at a time when the galaxy, or its precursor fragments, had just begun forming stars, when only a few supernovae had seeded the environment with heavy elements. Some of the halo's metal-poor stars are among the oldest ever found, nearly 13 billion years old, dating back to within a few hundred million years of the universe's beginning. Some are so pristine in composition that they probably formed directly from the primordial gas enriched by only the very first stars, which were themselves long since gone. In their atmospheres, we see the faint chemical echoes of those first stars. These ancient stars wander the halo, individual embers from a time when our galaxy was in its infancy. In contrast, stars in the thin disk, like our Sun, tend to have much higher metallicity. The Sun contains about 2% of its mass in elements heavier than helium. That may sound small, but it's vastly higher than the metal fraction in those halo stars. It tells us the Sun is a relatively latecomer, born around 4.6 billion years ago, in a galaxy already enriched by countless earlier stars. By then, previous generations of stars had lived and died, seeding the interstellar gas with elements that would become the iron in our blood, the calcium in our bones, the silicon in the rocks of Earth. We truly are made of this star stuff. The oxygen we breathe, the carbon in our cells, all were forged in stellar furnaces long before the Sun's birth. Each of us carries pieces of ancient stars within us. The thin disk stars, especially in the inner regions, show evidence of ongoing chemical enrichment. Even within the disk, we observe that older stars have lower metallicity and younger stars have higher. It's as if each new generation of stars inherits the ash of previous generations, the heavy elements they produced, making each successive generation a bit richer in metals. Between these extremes lies the population of the thick disk and inner halo, which often have intermediate metal content and unique chemical signatures. Many thick disk stars have an enhancement in alpha elements, like oxygen, magnesium, relative to iron, suggesting they formed rapidly from gas, enriched mostly by short-lived massive stars. which produce lots of alpha elements in supernovae before longer-lived stars had time to add more iron. This hints that the thick disk formed in a relatively quick, dramatic episode, perhaps triggered by a violent event. All these chemical clues tie into kinematic ones, how those stars move. Halo stars, as noted, often have very elliptical or inclined or even retrograde orbits, distinguishing them from the orderly rotation of the disk. The thick disk stars do rotate in the same overall direction as the thin disk, but with a bit more randomness. Some lag behind, some lead, and they have higher vertical motions. When we examine these patterns carefully, we find evidence that the halo itself might contain substructures, remnants of smaller systems. One clear sign emerged from our trove of Gaia spacecraft data. A large number of halo stars share a common motion pattern, moving on radial orbits, going out and back in, and possessing similar metallicities. They stand out as a coherent group amidst the halo field. Astronomers now believe that about 8 to 10 billion years ago, the Milky Way had a dramatic encounter with a smaller galaxy, a merger that delivered a huge influx of stars and dark matter. This invading galaxy was torn apart by the Milky Way's gravity. Its stars were strewn into the halo on those radial orbits, and its substance likely puffed up the pre-existing thin disk of the Milky Way into a thicker disk. The evidence of that event still persists in the motions and chemical makeup of stars, sometimes poetically dubbed the Gaia sausage or Enceladus stream, names given to that distinctive clump of halo stars. Such patterns in stellar motions remained hidden until modern sky surveys provided precise velocities for so many stars. Suddenly, this ancient collision stood revealed in our data, a fossil galaxy within the Milky Way's halo. In addition to that major merger, the halo holds hints of other, smaller mergers. We have found numerous star streams, long filaments and clumps of stars sharing common velocities and trajectories. Each stream is the stretched remains of some smaller object, maybe a dwarf spheroidal galaxy or a globular cluster that ventured too close and was pulled apart. The Sagittarius stream is one example we've mentioned, the ongoing disruption of the Sagittarius dwarf galaxy. There are others, the Helmi stream, the GD1 stream, and so on, each corresponding to a different accreted system. Even some globular clusters seem to belong to certain groups associated with past mergers. For instance, a set of outer halo clusters likely came in with the Sagittarius dwarf, while another set might have been part of the hypothesized Gaia Enceladus galaxy. By charting which clusters and stars came from where, we are assembling something like a family tree of our Milky Way. Which parts were original, which were adopted or acquired over time. Even within the disk itself, the stars carry memory of the galaxy's history. There are stars in the solar neighborhood that have much lower metallicity than the Sun, yet move in the plane. Perhaps they migrated here from farther out in the disk, or are part of the thick disk population. Some stars have peculiar chemical ratios that set them apart, suggesting they might have formed in an environment outside the Milky Way, say in a dwarf galaxy, and later been assimilated. The disk, especially the outer disk, contains subtle ripples and arcs of stars that might be the result of recent perturbations. Possibly, the disk ringing like a bell after the passage of a satellite galaxy. One such feature is the Monochoros ring, a ring of stars rippling around the outer disk. It might be debris from a swallowed dwarf, or simply a wave in the disk induced by a satellite's gravity. Using all these clues, astronomers have begun to sketch the Milky Way's history. In the beginning, over 12 billion years ago, our galaxy's progenitors were likely a few smaller protogalaxies, made mostly of hydrogen, helium, and dark matter. These clumps merged early on, building a stellar halo and the first, relatively small primitive disk. Many of the globular clusters formed in this era, either within the protogalactic fragments or in the nascent Milky Way. Then, around 10 billion years ago, a significant merger, Gaia Enceladus, delivered a load of stars to the halo and possibly created the thick disk, by dynamical heating. Subsequent to that, the Milky Way spent the next several billion years evolving more quiescently. Gas continued to fall in, some perhaps from intergalactic filaments, some from smaller infalling dwarfs, and the thin disk grew outward, forming stars steadily. Our galaxy's spiral pattern likely persisted and perhaps reformed at times, and a bar may have formed a few billion years ago as the central disk became unstable and elongated. Minor mergers continued. Even today, the Sagittarius dwarf galaxy is being consumed, and the large and small Magellanic Clouds, our prominent satellite galaxies, are interacting with our halo and will eventually merge as well. Through all this, star formation has cycled on and off, enriching the interstellar medium further with each generation. The Sun's birth about 4.6 billion years ago came at a relatively calm time in the Milky Way's life, long after the major mergers, in a galaxy that already had a well-defined spiral structure and plenty of heavier elements. In a sense, our galaxy is a mosaic assembled from many pieces, some formed in-house, others acquired, and this process is ongoing. Even as we speak, the Milky Way is not done changing. It is surrounded by dozens of satellite galaxies, like the Magellanic Clouds and many ultra-faint dwarfs. Some of these will eventually merge into it, and looking to the far future, our galaxy itself is on course to merge with the Andromeda Galaxy, M31, some 4 billion years from now, an event that will drastically reshape both into a new, larger galaxy. The Milky Way's story is still unfolding, and we happen to find ourselves at a rather calm chapter in that long tale. In reading the stars and their motions, we have essentially become galactic archaeologists. We take the present evidence, the trajectories and elemental makeup of stars, and infer the past events that produce them. It's astonishing that here, on a little planet, we can piece together events that occurred 10 billion years ago and tens of thousands of light years away. And yet, piece by piece, we have done exactly that. The result is a narrative of construction and transformation. Our Milky Way grew by accretion and mergers. It has been both the cannibal and the cannibalized. It has swelled over time with the infusion of fresh material, and it continues to evolve. It remembers the violence and fireworks of its youth in the motions of old stars, and it wears the accreted stars of smaller galaxies as part of its halo, like scars or trophies. We have come far. From wondering what the Milky Way's band was in the sky, we have arrived at a point where we can describe its structure, its composition, its movement, and even its history. And perhaps, on some distant world orbiting a star on the far side of the Milky Way, there could be other beings looking up at this same band of light from their vantage point, asking similar questions. They too would face the challenge of understanding the Milky Way from within, unaware of our existence, just as we were long unaware of theirs. If such observers exist, then the mystery of our galaxy is a shared one, a grand puzzle that beckons to any creature with the will to look up and wonder. About 100 years ago, we didn't even know for certain that anything lay beyond the Milky Way. This very question was the subject of the Great Debate in 1920 between two leading astronomers, Harlow Shapley arguing that the Milky Way comprised the whole universe, Heber Curtis contending that the spiral nebulae were outside our galaxy, perhaps galaxies themselves. It was only in 1924 that Edwin Hubble measured the distance to the Andromeda Nebula and found it to be far, far beyond the Milky Way. In that moment, our perspective expanded immensely. The Milky Way was revealed to be just one of countless island universes. A large galaxy, yes, but hardly the only one. Our galaxy went from being the entirety of the cosmos to being one member of the local group, our small cluster of galaxies, similar in stature to Andromeda. Today, with modern instruments, we have even measured the mass of our galaxy and Andromeda. The Milky Way is approximately on the order of 1 trillion solar masses in total,
That's 1,000 times the mass of our Sun. Though stars and gas are only about 10–15% of that. The rest is dark matter. Andromeda is of comparable mass and size, and contains perhaps 1 trillion stars to our few hundred billion. Knowing this places our galaxy in context. Not only is the Milky Way not the entire universe, it isn't even the biggest galaxy in our local neighborhood. Yet for us, the Milky Way is uniquely significant. It is home. When we gaze at that Milky Band, we are looking into the structure that made us. Our Sun's existence, the heavy elements that form our planet and our bodies, the gentle environment that shelters life. All these are products of the Milky Way's long evolution. We owe our very existence to events that happened in our galaxy long before the Earth formed. Ancient supernovae that synthesized iron, for example. We are connected to the Milky Way profoundly. We are a part of it. To truly appreciate our galaxy, it helps to use more familiar analogies. To illustrate another way, imagine the Milky Way as an enormous city of stars. The spiral arms are like brilliant avenues, lined with hot young stars that shine like neon signs, bustling with nebula where new buildings, stars, are under construction. The central bulge is a crowded downtown, full of old red giants that glow like streetlights in an ancient district. At the very center, a massive city hall, black hole, governs the motions around it. The halo forms the quiet suburbs, sparsely populated by a few old stars and clusters, far removed from the busy streets of the disk. Throughout this stellar metropolis, things are constantly changing. New structures rise, stars form, and old ones crumble, stars die. Sometimes a neighboring town, dwarf galaxy, gets absorbed into the city limits, adding its stars to our population. Yet despite all this hustle and transformation, the city of the Milky Way maintains its overall character through cosmic ages. We, living on Earth in a calm neighborhood, the Orion Spur, off one of the major arms, are citizens of this galactic city. We witness its grand traffic flow around us and participate in its story, even as we go about our humble lives. Galaxies are not static backdrops. They are active, dynamic systems. The Milky Way is an ecosystem of constant change, a cosmic forest in which stars are born, evolve, and die, enriching the soil, the interstellar medium, for the next generation. Stars form in the spiral arms, live their lives, the most massive burning out quickly, the smaller ones enduring longer, and eventually end, quietly if they are sun-like, dramatically if they are huge supergiants. When a massive star dies, it goes supernova. The explosion not only disperses heavy elements into space, but its shockwaves can jolt nearby gas clouds, possibly triggering the birth of new stars. This feedback loop, stars giving back matter and energy to the galaxy, is crucial. Through this feedback, the galaxy redistributes energy and matter and regulates its star formation. Stellar winds and supernova blasts carve bubbles in the gas, sometimes clearing out regions and halting star formation temporarily, other times compressing gas elsewhere and stimulating more star birth. It's a self-balancing act. At present, the Milky Way's star-making pace is relatively sedate. It converts only a few solar masses of gas into new stars each year on average, perhaps 1 or 2 new stars like the Sun, and a few more lower-mass stars annually. By cosmic standards, this is a gentle rate. It's enough to keep the spiral arms adorned with some bright newborns, but not so high that we burn through all our gas quickly. There are starburst galaxies in the universe forming hundreds of stars per year, blazing furiously for short periods, and then quenching when their gas is exhausted or blown out. But our Milky Way seems to prefer a steady, sustainable cadence of star formation. This moderate behavior ensures that the Milky Way's gas supply will last many billions of years to come. Over time, each generation of stars changes the composition of the galaxy's gas a little more, enriching it with heavier elements. The young stars forming now carry within them the products of countless stellar lives before them. In this way, the galaxy's chemistry evolves, the metallicity of stars increasing as the cosmic soil becomes more fertilized. Our Sun, for instance, has far more heavy elements than the first generation of stars, telling us it formed in a used, enriched medium. This ongoing enrichment will continue with future generations. Meanwhile, the whole galaxy is gravitationally interacting with its environment. Our Milky Way is orbited by dozens of satellite galaxies. Some are fairly large, the Large Magellanic Cloud and Small Magellanic Cloud, visible to the naked eye from the southern hemisphere, each a few percent the mass of the Milky Way. Others are extremely small and faint. The ultra-faint dwarfs discovered in recent years, some of which have only a few thousand stars. These satellites move around the Milky Way, and our galaxy's gravity pulls on them. Sometimes, as we've seen, it tears them apart, like the Sagittarius dwarf. The Large and Small Magellanic Clouds, LMC and SMC, are currently close by and interacting with our halo. Their gravity may be raising tides in our disk and halo, and our gravity is stripping gas from them, producing the long Magellanic stream of gas that trails behind them. In recent years, astronomers have discovered more and more of these faint satellites. Dozens have been catalogued, and more continue to be found as our surveys improve. The Milky Way's entourage of satellites is more extensive than once thought. These interactions have effects. The LMC, for instance, with its substantial mass, around 10% of the Milky Way's mass, is tugging on our galaxy's halo and might even be shifting the center of mass slightly. It's likely contributing to the warp in our outer disk. Our disk is not perfectly flat, but bent, and the gravity of the Magellanic Clouds could be one cause of that warp. The infall of the Sagittarius dwarf seems to correlate with bursts of star formation in our disk. Indeed, some studies suggest that about 5 billion years ago, and again, about 1 billion years ago, Sagittarius's close passes perturbed our galaxy and triggered higher star formation rates, possibly even triggering the formation of our Sun around one such time. Thus, the satellites have likely influenced the Milky Way's evolution. Like dancers around a larger partner, their gravitational tugs send subtle ripples through the Milky Way's disk and halo. Our galaxy will continue to grow by merging these satellites. In the far future, as mentioned, it will experience the ultimate merger, with the Andromeda Galaxy, and likely also the Triangulum Galaxy, M33, a smaller member of our local group. In about 4 billion years, Andromeda and the Milky Way will draw together, their mutual gravity distorting both. Perhaps long tails of stars will be flung out, and over a couple of billion more years, they will coalesce into a single elliptical galaxy, sometimes dubbed Milkomeda. The night sky of Earth, if Earth is still around and life still here, would change drastically during that merger, with new patterns of stars and intense star-forming fireworks for a while. Eventually, the two spirals' identities will be lost in a new, larger galactic system. Thus, even the Milky Way is impermanent on cosmic timescales. Through all of this, one cannot help but feel a sense of narrative, a sense that the Milky Way has lived a life of its own. We, as sentient beings within it, have only just become aware of that grand story. It is a bit like coming of age and suddenly learning the history of your vast family or nation, except our nation is a galaxy 100,000 light-years wide and 13 billion years old. It took remarkable scientific sleuthing to deduce this history. It is a testament to the human mind's ability to reason and infer that we can reconstruct events so remote in time and space. Our map of the Milky Way, therefore, is not just a static picture, it's an unfolding story. It shows a current snapshot, spiral arms, bar, etc., but also contains clues of how that snapshot came to be. By studying other galaxies which we can see from the outside, we gain further insight into stages of our own. We see galaxies in various merger stages, or starburst phases, or with different proportions of components, and we realize the Milky Way likely went through similar phases, or will in the future. Our understanding of galaxy formation has, in turn, fed back to refine our model of the Milky Way. Mapping our galaxy from the inside has truly been one of humanity's great scientific achievements. Over the past century, we progressed from having only a vague idea of our place in the cosmos to having a detailed mental construct of our entire galaxy, something no one observer can ever see in full. It required meticulous data collection and clever deduction. It's as if we have mapped a vast labyrinth by walking through its corridors and feeling our way, since we cannot rise above it to see the whole. And somehow, we succeeded. Mapping our galaxy from within stands as a triumph of human curiosity and intellect. Even as we gather more data and refine our models, we remain observers trapped inside the system we study. We will always be looking outward from within, and that inherently limits our perspective. There may always be features we cannot perceive directly, perhaps some subtle pattern in the distribution of stars that is too broad to recognize from inside, or some effect that requires an external view. We compensate with ingenuity and indirect methods, but there is something profound about this limitation. We are part of the very thing we are trying to understand. It is interesting to note that while we cannot see our galaxy from outside, observers in other galaxies can. To an astronomer in the Andromeda galaxy, for example, the Milky Way would appear as a faint, elongated spiral nebula in their sky, much like Andromeda appears to us. They could capture photos of our galaxy's grand design in a way we cannot. And conversely, we see Andromeda's spiral structure clearly, while the Andromedans, if any exist, must deduce it from the inside. In a cosmic sense, we and Andromeda serve as mirrors for each other. By studying other galaxies, we've come to understand our own, and in the future, the Milky Way and Andromeda will merge and no longer be separate, their destinies entwined. In about 4 billion years, as mentioned, this merger will begin, an event that future astronomers, perhaps not human, perhaps whatever beings exist then, will witness and record. The Milky Way as we know it will evolve into something new. But those changes are far in the future. For countless generations to come, the Milky Way will remain the majestic barred spiral that cradles our sun and its planets. Our explorations have transformed that misty band in the night from a source of speculation and myth into a mapped and modeled galactic system. Yet, even as we explain it scientifically, the Milky Way has lost none of its ability to inspire awe. If anything, knowing what it truly is makes it more amazing. The simple band of light has become a vast spiral of stars in our mind's eye. The tiny points of light have become distant suns with their own worlds. The dark gaps have become nurseries holding unborn stars. The slight glow on the horizon of vision has become the memory of ancient mergers and the halo of an invisible mass. So the next time you find yourself under a truly dark sky, take a moment to let your eyes wander along the Milky Way's gentle glow. Think of all the stars hidden in that band, the clusters and nebulae, the spiral arms wrapping around, and the far-off center with its secrets. Consider the journey that light has made to reach you, and the journey we have made to understand what it means. In that quiet moment, you are connected to our galaxy in a profound way, an observer within it, aware of its vastness and complexity. Think of how many before you have stood under this same sky, seeing that milky arc and wondering what it was. Now you carry the answer to their wonder. The Milky Way is our home galaxy, breathtaking in its scale, dynamic in its story, and you are a part of it. The hazy band of light ceases to be just an appearance. It becomes a personal encounter with the cosmos, a bridge between you and the ancient, ongoing story of our galaxy. It is a reminder that even as we strive to explore and understand the universe, we are already deeply home within it, nestled among the stars of the Milky Way, forever looking out and in.